Hello everyone, how are you all? Just let me check. Yes, it's fixed. So just tell me that whether I am visible and audible or not, and then I will start the class. Just wait for a second. Let me check if I am audible and visible. Yeah, so it's working perfectly now. So basically, today, obviously, we are doing an important thing for all of you, which is basically focusing for your um, PUC exam, right? So your second PUC FA-1 exam is coming, and that's why we are going to do a long marathon. So you have four chapters, third 3.5 chapters, I will say. Electric charges and field, electrostatic potential and capacitance, current electricity, and moving charges and magnetism, but it is not there completely according to the board's prescription. The syllabus that is given by the board, electric field due to a current carrying coil, that is the last portion. And if your college is doing complete chapter, that is up to your college, but we will cover these four chapters, so don't worry. Today I will be discussing the two most important chapters, electric charges and fields, as well as electrostatic potential and capacitance. And what will be the format will be question answer. We will be solving a lot of questions, over 55 57 questions, I think, total, including both chapters. So lot of questions, including MCQs, fill in the blanks, as well as 2 marker, 3 marker, 5 marker derivations, 5 marker numericals. Everything will be covered for these two chapters in today's session, and in the next session I will complete the remaining two chapters. So all chapters will be covered through this session, right? Now, let me tell you what is the question paper pattern. Many of you sometimes be confused, sir. This is a 35 marks paper. So, what will be the paper pattern? Generally, 70 marks pattern is different than 35 marks. So, generally, what is the pattern is there will be 7 MCQs, 7 MCQ question. Okay, there will be 3 fill in the blanks. Now, some for some subjects it might change, but for physics this is the general pattern. 7 fill in the blanks, 3 7 MCQs, 3 fill in the blanks. Okay, then there will be 2 questions of 2 questions of um, 2 marker, 2 questions of 3 marker. Okay, there will be 2 derivations of 5 marker, and there will be one numerical question of 5 marker, right? So this is the general pattern of 35 marks. So if you add them, 7 plus 3 10, 10 plus 4 is 14, 14 plus 6 is 20, 20 plus 10 is 20 plus 10 is 30, 30 plus 5 is 5 marks. So total 35 marks. This is the general pattern for 35 marks. Your unit test paper, first unit test or FA test, FA-1 test, or first quarterly test, whatever you call it. This is general pattern for a 35 marks physics paper. Okay, and if you have any other questions, you can ask me in the chat directly. I will try to answer them as much as possible. Right, now let's start with the first chapter, electric charges and fields, and we will start with MCQs. So MCQs are tricky because what happens, you practice a lot of questions, especially for PU board. You practice a lot of questions, but you do not go into deeper into the theory portion, and you are not well versed with the MCQs. So that's why, if you get time, I request you read the NCRT chapter at least once, so that if there are some in between questions, in between line questions are being asked, you should be able to answer them. So read NCRT textbook at least once for MCQ questions at least. Okay, now let's see the SI unit of electric charge. This is the questions are not made by me. It is done either taken from your question banks, or from previous year papers which questions are being asked regularly. So don't think that this question is easy, the other question is difficult. Why it is so? Because the questions in board paper, they are always not same. Sometimes it is easy, sometimes it is difficult. Okay, so the SI unit of electric charge is coulomb meter, coulomb per meter, coulomb per coulomb. So charge, SI unit of charge is obviously coulomb. SI unit of charge is obviously coulomb. No doubt about that. Next question. The total electric flux through a closed surface in air is equal to 1 by epsilon naught times the total charge enclosed by that surface. This is statement of. So what is this statement? So total charge through a closed surface, total charge, total electric flux through a closed surface. Okay, total electric flux through a closed surface is charge divided by epsilon naught. So this is the formula for Gauss's law. So Coulomb's law, no. Gauss's law of magnetism, no. Gauss's law of electrostatics, yes. Okay, and obviously not Ampere's circuital law. So correct answer is Gauss's law in electrostatics. Next question. Electric field due to an electric dipole at a distance small r on its axis of the dipole is. So electric field due to an electric dipole at a distance small r on the axis of the dipole. Now this question was asked in KCET exam as well. Few years back, 7-8 years back, this question was asked in KCET as well. Okay, so electric field due to an electric dipole at a distance small r on the axis of the dipole is. So electric field on the axis of a dipole is inversely proportional to square cube of distance r. Okay, so inversely proportional to r cube. Normally for a point charge, remember, for a point charge, if the charge is a point single charge, electric field is given by kq upon r square. K is Coulomb's constant. But for a dipole, the formula changes and the electric field for a dipole on its axis, is given by 2p k 2p upon r cube. Okay, and if you are talking about equatorial plane, same thing, dipole on equatorial plane, magnitude of that is given by k into p upon r cube. Okay, so this is the formula that you need to remember. For a dipole, it is no longer proportional to 1 by r square, it is proportional to 1 upon r cube. So inversely proportional to r cube. Okay, so this is the answer for dipole. Next, the SI unit of electric flux is. So let us understand what is electric flux. Electric flux, hello Richard, hello. So what is electric flux? Electric flux is basically given by, if you remember, electric flux is electric field through area. Okay, electric field multiplied by area is the electric flux through a surface. Closed surface or open surface does not matter. Gauss's law is applicable for closed surface only, but normal electric flux can be for open surface as well. That is one important point to remember. Now flux is electric field into A. There is a cos theta component, but cos theta is a dimensionless quantity, so we are not writing because we are trying to find unit or dimensions. In case of dimensions also, you can use the similar concept. So what is electric field? Unit of electric field is Newton per Coulomb. I am writing it like this. Per Coulomb means division, right? Newton per Coulomb means what? Newton per Coulomb means Newton divided by 1 Newton divided by 1 Coulomb. So I am writing Newton by Coulomb. What is area? A is area. So what is area? Area is meter square, right? So what is the combined unit? Combined unit is Newton meter square per Coulomb. Okay, Newton meter square per Coulomb, or you can write this as Newton meter square c to the power of -1. So if you see that only one unit matches with that, so they have written Newton per Coulomb into meter square, so the unit identification is much easier over here. So this one denotes the electric field, this one denotes the area. So obviously option C is the correct answer for this question, right? Now next is charges are conserved for open system, isolated system, any system, no system. Okay, remember charges are conservative quantity. If you remember the properties of charges, it says that charges are conservative quantities, but charges are conservative for only isolated system. Only isolated system, do not mark any system. Okay, remember that. Also a similar question might be asked for Gauss's law as well. Gauss's law is applicable only for closed surface, not for any surface. Yes, any type of closed surface, but surface has to be closed. Okay, similarly charges are conservative only for isolated system, not for any system. Okay, do not make that mistake. I have seen students, they believe that charges are conservative, that is a property, so it should be for any system. No, it is only for isolated system. If the system is not exchanging anything with the surrounding, then it is called an isolated system. That means whatever is inside, that will remain like that. It is not coming out or going in anything. That's why it is called isolated system. Isolated system, charge is always conserved. Sir, for unit test, 5 mark is from which chapter? Hemant Kumar. So I will, as I mentioned in the past also, if you have seen my fixed question videos, okay, 5 marker question, there will be 3 5 marker question. Okay, 3 5 marker question and 2 numerical questions. Out of the 3 5 marker questions, you have to answer any 2, and out of the 2 numerical question, you have to answer any 1. Now 5 marker question will be asked from the chapters electric charges, electric potential, current, electricity, moving charges. All chapters are important for 5 marker question. Out of the 4 chapter, any 3 5 marker question will be asked. Okay, now if they are not giving any derivation from the moving charges chapter, then probably first 3 chapters, all 3 chapters are important for 5 marker derivation. Okay, but in board exam, in respect of board exam, if you consider the board exam, if they are closely following the board pattern, then from the first 2 chapters, 1 numerical, 1 derivation, any one of the chapters. It is not given in the board paper also. They only mention that from first 2 chapters there will be 1 numerical, 1 derivation. But if numerical is coming from electric charges, then derivation will be asked from electric potential. Similarly, if the derivation is asked from electric charges, then numerical will be asked from electric potential. That is confirmed. Okay, so from the first 2 chapters, 1 derivation, 1 numerical you are guaranteed to get. In current electricity, you are going to get 1 numerical, 1 derivation, that is also guaranteed. Okay, but from moving charges, numerical questions will not come, but there is a chance they might give you a derivation, because you have a 1 major derivation from that chapter. So might be they might give you the derivation, they may not give you, but that for midterm, generally board pattern can be followed, may not be followed. It also depends on your college. It depends if you are using the district papers. District papers varies from district to district as well. Okay, so there is no guarantee, but you have to practice derivation from all 4 chapters. There is no options. But numericals, first 3 chapters if you practice, you will get 1 numerical. Now current electricity generally can be sometimes tricky numericals wise. If you are not practicing enough numericals from that chapter, can be difficult. So first 2 chapters numericals you have to practice anyway, right? I hope that helps, Hemant. Rama, there will be two marathons. This is part 1, and there will be 1 more marathon. If you follow both the marathons, yes, FA-1 you will score well. That is my guarantee. Okay, it happened in the past, it will happen this year also, but you have to follow it properly, right? And if you want to study from us directly in the live classes throughout the week, we have launched our Pariksha Veera batch. Okay, it is a paid batch, but we are coming live. We are teaching for PUC as well as KCET. So this is a combined batch. Combined batch means it's a integrated batch. where KCET as well as PUC, both chapters, both aspects are being covered, and we are giving you 110 hours per subject. Okay, you are going to get 20 plus tests for your KCET preparation per subject. Again, teacher notes, assignment, unlimited DPP generator. So if you want to practice more questions, that will also be provided. Okay, and it will be delivered on our web app. The price for the batch is 3499. If you are interested joining the batch, the link is given in the description. Right now, biology and mathematics classes are over for the day, and chemistry classes is going on in the batch. So if you are someone who is looking for a integrated way, I don't want to study separately for boards and KCET, then definitely you should join this batch. The batch is live, and the link to join the batch is given in the description. But don't worry, if you don't want to pay also, I will give you another super duper thing as well. Don't worry. Now, next question, the value of basic unit of charge is. So, value of basic unit of charge is, what is this? It is 1.6 into 10 to the power of minus 19 Coulomb. 1.6 into 10 to the power of minus 19 Coulomb. It's like an eye catcher, because you might think that okay, 9 and 6 are shifted in this. So might be it, even though it is very common, some students make mistakes because they are super confused in the exam hall whether it is minus 19 or minus 9. So those kind of confusion will come in your head if you have not studied it. So remember, it is 1.6 into 10 to the power of minus 19. That is the basic value of charge. Okay. Next, two electric field lines can never intersect, always intersects, may intersect, always perpendicular. Two electrical field lines, they will never intersect, never ever intersect. Okay, if they are supposed to intersect, they will rearrange themselves so that they don't have to intersect each other. Okay, so intersection does not happen for electric field lines. They can never ever intersect. This question is from the properties of electric field lines. Okay, now next is the SI unit of surface charge density is. Surface charge density is what? Surface charge density is given by the symbol sigma. This is the symbol sigma. Surface charge density means the total charge on the surface divided by surface area. So suppose I have a surface, okay, I have some charge on the surface. Okay, it can be positive, it can be negative. For now I am showing you positive charges. Suppose I have a surface, I have some charge on it. The surface area, how to calculate? If it is a square plate, you can do the length into breadth. If it is a spherical surface, you have to use 4 pi r square. So based on the nature of the surface, design of the surface, you have to calculate the area. And if the total charge on the surface is Q, the area is A, then surface charge density is Q upon A. So what is the unit of Q? Q is charge, so its unit is Coulomb. Area is meter square. So unit of surface charge density is Coulomb per meter square. Many students confuse between surface charge density, line charge density, and volume charge density. So line charge, remember, line charge is given by length by charge by length. Charge by length, which is Coulomb per meter. Okay, surface, already shown you, surface is given by Q upon area, that is Coulomb per meter square, and volume charge density. These three are three different quantities, and any one of them can be asked. I have given surface charge here. That does not mean that in the exam, if the surface charge density question is not asked, you will say, sir, volume charge was asked, not surface charge. So just remember, volume charge is given by the symbol rho. It looks like a P, and it is Q upon V, which is unit is Coulomb per meter cube. So there are three different quantities having three different units. Okay, even though they are very similar, but they are very different as well. Line charge density, surface charge density, volume charge density. Coulomb per meter square, Coulomb per meter cube. Okay, you have to remember all these units. Okay, if you have studied it in the past, fine. If you have not studied it, now it's the time for you to remember these things. And notes, everything, if you are wondering, I will tell you how to get the notes as well. Don't worry. SI unit of electric field is, electric field, I already told you, electric field is given by force by charge. Okay, that is Newton per Coulomb. So its unit is Newton Coulomb to the power -1. So SI unit of electric field is Newton per Coulomb. The angle between the dipole moment and electric field at any point on the equatorial plane. So if you remember, if you have done the derivation, we will do the derivation, so don't worry. If you have not done it, no issues about it. Okay, so suppose this is positive charge, this is negative charge. Dipole moment always points from negative charge to positive charge. This is the direction of dipole moment. And on the equatorial plane, the net electric field always points in this direction. This is the net electric field on the equatorial plane. Okay, and as you can see, the dipole moment is in this direction, the electric field is actually in opposite direction. So if two vectors are acting in the opposite direction, what is the angle between them? Angle between them is 180 degrees. Does not matter, they are not at the same point, but main thing is the directions are opposite. That means the angle between them will be 180 degrees, not 90, not 0, nothing else. If the same question is asked, they ask you that dipole moment on the axis. Dipole moment on the axis. Suppose this is my negative charge, this is my positive charge. Dipole moment is negative to positive. Electric field will also be in this direction. Okay, so this is the axial dipole electric field. So in case of axial case, angle will be 0 degree. For axial, theta is 0. For equatorial, it will be 180 degree. For any other position, it can be any angle. Between 0 and 180, it can be any angle possible. Okay, so remember this. This is very interesting, important question. Now let's do some fill in the blanks. One of the basic properties of electric charge is. So let's see how to do the fill in the blanks. Fill in the blanks is also can be complicated if you are not careful. There will be some options which can be very close to each other. Pratibha, Rajesh, so it will be done on Saturday. Saturday we are doing current, electricity and moving charges and magnetism. Right, Pratibha? Now, one of the basic properties of electric charges. So what is the basic property of electric charge? Let's see the, always after reading the question, read the options. And remember, one option can be used only once. So there will be some, in midterm, it still be, sorry, not midterm. In FA-1, it can still be easier because only 3 fill in the blanks will be given. But in midterm, in your pre-board and your board exam, there will be 5 fill in the blanks. So that can be little tricky. If you are not careful, there will be 2 options which are very close to each other. And if you are not careful, you will make, if you just reverse the order, that means 2 fill in the blanks are gone. Okay, one mistake gives you, cost you 2 fill in the blanks. So be careful, double check it, triple check it before answering. You will get enough time to finish the paper. So don't be in a hurry. Okay, and you always keep some time for MCQs and fill in the blanks. Okay, and you remember, fill in the blanks, MCQs all have to be written in the front page, not in the behind at the end of the papers. Okay, so if you are not attempting MCQs at the beginning, leave the first 2 pages blank. Okay, cover it later on. Okay, remember this. This is very important point to remember. One of the basic properties of electric charge is never, obviously does not make any sense. First check if it is making any sense language wise. So one of the basic properties of electric charge is never, obviously not making sense. Dipole is also not making any sense. Quantization. So quantization is a property of charge. So this makes a sense. Maybe this is the answer. We will verify it once more, okay, by checking other options. So one of the basic properties of electric charge, vacuum, again does not make any sense. Basic properties of charge, zero, does not make any sense. Basic properties of charge, always. This is also does not make any sense. So only option that is suitable is quantization. So we will just write quantization over here, okay. And immediately as soon as you fill this option, you mark or underline this option because it is already done, okay. When checking the other fill in the blanks, we do not need to look for this option again because this is already filled. Next, a pair of equal and opposite charges q and minus q separated by a distance 2a is. So now we have seen the options once. So we know that this is called a dipole. So dipole will be marked again. So this is called a dipole. And we will mark dipole. We will underline dipole. Next question. The electrostatic force between two charges is maximum. The electrostatic force between two charges is maximum in never, vacuum, zero, always. So we know that electrostatic force is maximum in vacuum or in air. So here vacuum is given. So we will write vacuum. Right? We will write vacuum. And immediately we will also underline the correct option. Electric field inside a charged spherical conductor is. So electric field inside a charged spherical conductor, if you are considering a spherical conductor or a shell, electric field inside a charged conductor is always zero. Electric field inside a charged conductor is always zero. Right? All the charges always reside on the surface of the conductor. So no charges are present inside the conductor. That's why if you apply Gauss's law, electric field will be zero. That means electric field inside a charged spherical conductor, no matter it's a spherical, cubic or any metallic conductor, electric field inside a conductor will always be zero. Even though always is given an option, but here always is not making any sense. So answer will be 0. So it will be 0. Next question. Two electric field lines will dash cross. Now this is a tricky if you don't know the answer, because two electric field lines will never cross, two electric field lines will always cross. So both are making sense English wise. If you are considering only language, both sentences are grammatically correct, okay, and it's making some sense. But if both sentences are correct or not, that is your knowledge that you have to apply. So two electric field lines will never cross, okay, they will never ever cross. That is the properties of electric field lines. So answer will be never over here, okay. The property of electric field lines says that two electric field lines will never cross, okay. Now let's move on with 2-marker question. Now this is one of the very important 2-marker question. State and explain Coulomb's law or write Coulomb's law in vector form. Both questions have been asked multiple times throughout the history of PU, be it FA-1, midterm, pre-board, final. Every time this is one of the most favorite question of the teachers and of the board as well, okay. So you can expect one of these questions can be asked. Now answer looks similar, there is a difference between the answers, I will tell that as well. So if it is said state and explain Coulomb's law, you need to write only the theory portion, okay. You need to write the statement, then mathematical form. Mathematical form can be vector, can be scalar, does not matter, but if it is being asked vector, then statement is not required. Instead, this diagram is required. Remember, I will show you the diagram as well. So first, let's see the diagram. Statement. Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between them. The force is acting along the line joining the charges. So this is the statement of Coulomb's law. Okay, this is the statement of Coulomb's law. If they say state and explain explanation, you can write the scalar form as well. I have given vector form to give you an idea that what will be the vector form of Coulomb's law. Now vector form, obviously if you just write this much, you will not get the full marks. Make sure you show a diagram. Diagram should be like this. There should be two charges q1, q2 separated by a distance. Okay, this one we will say r vector. This one we will say force on 2 due to 1, and this one we will say force on 1 due to 2. This is F12, this is F21. Now remember, in vector form you have to you have to show which force you are writing for. We are writing F12, that is this force, okay, and F12 equals to 1 by 4 pi epsilon naught q1 q2 upon r square into r cap. Okay, the vector this is the unit vector. Okay, and also this is exactly equals to negative of F21. This is exactly opposite of negative F21. That is very, very important point to mention in this equation. Okay, q1 and q2 point charges. Epsilon 1 is the epsilon naught is permittivity of free space, r is the distance between the charges, and r cap is the unit vector. So this is the vector form. In vector form, the diagram is must. Without diagram, you will not get the full marks, right? uh, Deepak, my voice here is at full volume. Okay, you check your device voice once more. Okay, I can show you my volume if you want. Okay, my voice here is maximum. Okay, you can I can show you the volume in this device as well. See, even in my device from where I'm seeing the chat, that is also very high voice. Okay, Deepak, check your device once, and if it is not working, I request you use earphones. That could be a little better option, or you can switch to a you wave version. Okay, wave open the YouTube in the wave desktop site, and then you watch there. Maybe the volume can be increased from there. Okay, check your device volume. If it is not working, try the wave version or use an earphone. Sometimes maybe earphone can be tricky, and if you are not using, if you are already using an earphone, change the earphone. Listen to the class without earphone, because earphones can also be sometimes reduce the volume because of the there are some restrictions, right? Try all the ways. I think the volume is maximum from my end. Okay, my end there is not an issue with the volume. Okay, now let's continue with our question session. So this is the vector form. Very, very, very important question. This question, there is a high chance this question you will see in your FA-1 as well. Now next is state and explain Gauss's law in electrostatics. Now this question can be asked either as a separate question, or this can be asked as a starting question of a 5-marker derivation as well. Okay, this question can be asked as a 5-marker derivation, part of the 5-marker derivation, 1 plus 4 or 2 plus 3 kind of derivation, or this can be asked as a separate 2-marker question as well. Okay, so Gauss's law states that the total electric flux passing through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. So this is the statement. If it is coming as only 1 marker, as a 1 plus 4 in a derivation, you just need to write this statement. You don't need to show the mathematics. But if it is coming as a 2 marker separate question, then you also have to write the explanation. Okay, so flux is given by Q upon epsilon naught, and flux, what is flux? Flux generally is E dot dA, E dot A. Okay, but that is when the electric field is constant. If the electric field is not constant, then it can be written as integration E dot dA. Okay, we assume that if the electric field is varying, if it is varying with time, then we use integration. Integration you will learn in mathematics, okay, but for now you just remember, in this chapter integration is not that important, but you have to remember integration is important in the next chapter, by the way. But for now you remember, if the electric field, for example, if it is constant, you don't need the integration. If the electric field is not constant, then you need the integration. Okay, let's move on. Sketch the electric field lines of a force due to a point charge if charge is less than 0 or charge is greater than 0. Okay, so if the charge is less than 0, that is a negative charge. Less than 0 charge means a negative charge. Remember, less than 0 charge means negative. Okay, and greater than 0 means it's a positive charge. Just a trick question, whether you just trying to confuse you. So remember, for negative charge, all electric field lines always point towards the charge. All electric field lines always point towards the charge. Okay, so if there is an electric negative charge, then field lines will always point towards the charge. So arrows, basically diagrams are same. Diagrams are same, only the difference between the arrows. For negative charge, if you see, all the arrows are towards the charge. All the arrows are towards the charge. Okay. So basically, you take a scale, you draw a bunch of lines passing through the single point, and then you add arrows. This is for charge less than 0. Okay, this is for charge less than 0. For charge greater than 0, again same process, only difference is the arrows. Now for positive charges, the electric field line always point outward. So that means the arrows direction will also be outward only. Okay, so this is less than 0, this is greater than 0, this is negative charge, this is positive charge. Diagrams are almost same, except the direction of arrows are opposite. Next, the charges are additive in nature. Explain. This question was asked in, I think, last year's midterm paper in Bangalore South, but it can be asked in a your FA-1 exam as well, no matter from where you are watching. If a system contains 2 points, basically they are asking, explain one of the property of charges. Okay, because if they ask you what is the 3 basic properties, you just write charges are conservative, charges are quantized, charges are additive in nature, but you finish it there. But if they ask you what is the meaning of charges are quantized or meaning of charges are additive, then you may not be able to answer it. So that's why you have to careful. You need to remember a brief description of all the properties, and whenever the question comes, you have to write the descriptions as well. Okay, that will help you if the question is being converted into a 2-marker question. If a system contains 2 point charges Q1 and Q2, the total charge of the system is obtained by simply adding algebraically. Algebraically means 2 plus 2, 4. 2 plus 2, 4, that is called algebra. So Q1 plus Q2, that is, charges add up like real numbers, or they are scalars like the mass of a body. So if you add 1 kg mass with another 1 kg mass, total mass is 2 kg. Similarly here as well, charges are also simply added without needing to use any vector notation, because charges are actually scalar. Total charge of a system, you can give any example. I have given you given one sample example. You can write the example on your own. You don't need to remember the example or memorize the example. Just remember +1, +2, -3, +4, -5 random values. You just write. Some of them will be plus, some of them will be minus, and when you are trying to find the total value, just add them. Okay, and the C, if I have written 1, 2, 3, 4, 5. Some of them I have kept negative, some of them I have kept positive. Okay, so random values 1, 2, 3, 4, 5. Take one of them positive, two of them negative, like that, and then you just add them. You will get a value. So the result is basically addition of the charges. That's one example. This is an example. Okay, don't need to think, overthink. Do not try to remember this exact example. Example can be up to you. Only thing you need to remember: keep some positive, keep some negative, keep some charges. 3 or more charges are preferred. Okay, 3 or more charges. Make sure they do not add up to be 0. Okay, just for convenience, do not show that their addition are 0. So that means it does not matter at all. But yes, so once you are done with it, you just add them and you show the results. Yes, no, Mahantesh. Mahantesh, no. If the question is asked, say, write two properties of electric charges as a two marker, you don't need to explain it. But if it is asked as three marker, yes, you need to explain it. Okay. So that is the difference between a two marker and a three marker. If a two marker question is asked that write two properties only, then you may not need to explain it. But if the same question is asked three properties in three markers, then you need to line at least one line for each properties. Okay. Now, let's move on to three marker with the derivation. Derive the expression for torque on a electric dipole placed in an uniform electric field. For Gauss's law formula. Okay, you are asking about Gauss's law formula. So if they ask you write Gauss's law and explain the terms, you have to write it. Okay. So if they ask you Gauss's law, write Gauss's law and explain. Okay, so what we will explain? So basically explanation, either you have to draw a diagram and explain that charge is inside Q, electric flux is phi, then charge is given by flux is given by Q by epsilon naught, or you just write the mathematical formula and explain the terms. Okay, anyway, if you are explaining this, that means you have to explain what the terms represent. Okay, if I just say you that x is equal to p y, what does it mean? What does it mean? Does it have any meaning? No, right? Unless I say that okay, this is electric, this is current density, this is the conductivity, this is electric field, then it makes a sense, right? So you just cannot write any random equation and you can say this is the thing. So basically that is an, even though the teachers know, even though the equation that you are using are a standard, but still you have to explain for the teacher's clarification that you also know. So the exam paper you write is not to teach the teacher. It is to basically show the teacher that okay, I know it. That is the main thing. Okay, so many students actually think that why I have to write the answers because teacher knows everything, right? Actually, it has to show that you also know this. That's why you have to explain, right, Mahantesh? I hope that is clear. Now, derive the expression for the torque on an electric dipole placed in an uniform electric field. For this derivation, you have to draw a diagram. Okay, you have to draw a diagram. Diagram should be like this. There will be a electric field, uniform electric field. Okay. So direction of electric field lines are like this. And here you have, this is the electric field E. Okay, and here you have the dipole, which is kept some angle. Okay, so this is say negative charge. This is say positive charge. This is say angle theta. Okay, so you have kept a dipole like this. The distance of the dipole or the length of the dipole is 2a. Charge is q. Right? Now you have to find what is the torque acting on it. Now the dipole moment acting is from negative to positive. So this is the direction of dipole moment. So dipole moment is making an angle theta with the electric field. Very important. Remember, dipole moment has to make the angle theta. Do not change the direction of the charges arbitrarily. Now the positive charge, we know if there is an electric field like this, if you keep a positive charge will experience a force in the direction of the electric field. Similarly, if you keep in an electric field, if you keep a negative charge, the negative charge experiences a force in the opposite direction of the electric field. And what is the magnitude of that force? Magnitude of the force is given by Q into E. Right? So that concept we are going to use over here. So the negative charge will experience a force in this direction. Positive charge will experience a force in this direction. Okay, so this force is Q into A, Q into E. This is also Q into E, but in the opposite direction. Now, what is torque? If you go back to your first PUC, many of you have not studied it, I know, but if you just try to remember what is torque, torque is given by when two equal and opposite forces acts on a body, but at some distance, not at exactly at the same point. If two equal and opposite forces, suppose this is my body, okay, there is a force here, there is a force over here, this force say F, this is also F. So equal and opposite forces acting on a body, okay, then the expression for torque is given by take any one of the force into the perpendicular distance between the force. The perpendicular distance between the force, this is the expression for torque. Torque is force into displacement or distance, but here condition is there has to be two equal and opposite forces and the distance should be the perpendicular distance only. So this is the definition of torque. Now if you see that here there are two equal and opposite forces, but the distance between them is not perpendicular, it's making some angle. So you have to find the perpendicular distance between the charges. How to do that? For that we need to extend this line and draw a perpendicular. This distance is d. This distance we need to find out. Okay, this distance we need to find out. This angle is theta, so this angle will also be theta because they are similar angles, right? So similar angles are same. So if this angle is theta, this angle will also be theta, and we need to find this distance. So what is the torque? Torque is very simply torque acting on the charge is given by force into displacement or force into perpendicular distance. So now force here is Q into E. Force on both charges Q into E. Directions are opposite, but force are Q into E. What is the distance? To find the distance, we need to use the Pythagoras theorem or slight trigonometry. Okay, so trigonometry says that if this angle is theta, this is hypotenuse, this is my perpendicular, then perpendicular by hypotenuse is our sine theta. Okay, there is a mnemonic that you can remember. Some people have curly brown hair turned permanently black. Some people have sine is equal to perpendicular by hypotenuse, curly brown hair. Okay, curly means cos, brown hair means b by h, turned permanently black. Turned means tan theta, permanently black means p by b. Okay, so that is one. There I learned many other mnemonics from one of our student also. Okay, but I am not I don't remember it, but something about India and Pakistan, very interesting mnemonic. So if you remember that also, that is also okay. Now now let's see. So torque is equal to F into D. Now what is D over here? So D is basically, from this we can say D is basically H sine theta. Now what is H? This distance is basically 2a. This distance is 2a, right? So H will be 2a sine theta. You don't need to show it, but you have to understand why it is so. So the distance here turned out to be, the distance here is 2a sine theta. Okay, so now write it. Okay, or you can write Q into E into 2a into sine theta. Now we have to rearrange this something a little. So Q into 2a becomes separate and E becomes separate, and then we write sine theta. Now what is Q into 2a? So Q into 2a is called the dipole moment of the dipole. Q into 2a is called dipole moment of the dipole. So the expression for torque now becomes the dipole moment into electric field into sine theta. Okay, or PE sine theta. This is the scalar expression, but torque, dipole moment, electric field, everything is a vector quantity. So if you want to write them in vector form, then it becomes torque equals to P cross E. Torque equals to P cross E. So this is how you should do the derivation. Now, if you are doing the derivation, remember the diagram has to be explained briefly, and these quantities has to be declared. Okay, what is F, what is Q, what is E. Now, one objective question that might be coming from this one marker MCQ is that if the field is uniform, what will be the nature of the torque? So if the field is uniform, there will be a torque acting on a dipole, but there will be no net force. Field uniform means Q into E both are same value. So net force acting on the dipole will be uh, F minus F, so it will be 0. Net force is 0. Remember, net force is 0 in uniform electric field, but it will still experience as a torque. But if the field is non-uniform, for example, if the electric field is say like this, okay, now you keep a dipole. So one end of the dipole will experience more force, other end will be experiencing a less force. So in that case, there will be a net force as well as a net torque. Okay, obviously this is complicated. We will not be able to calculate it using our normal method. But yes, if the forces are, if the field is uniform like this, there will be no net force, only torque. If the field is non-uniform, there will be a force as well as a torque. So this is a very intelligent and important MCQ question that can also be asked from this same concept. Now, write 3 properties of electric charges. Additivity of charges. Charges can be added like scalars. So that's what I'm saying. In the exam, when I was checking the papers, student only write additivity of charges, quantization of charges, conservation of charges. They do not explain even a one single line. At least be courteous and write at least one single line to explain what does it mean. Additivity of charges. Charges can be added like a scalar, okay, or algebraically. What is the harm that if you don't write this one single line? Quantization of charges. All charges are integral multiple of smallest charge E, small e. Okay, all charges are integral multiple of smallest charge, small e. Conservation of charges. Total charge in an isolated system is conserved. Total charge in an isolated system is conserved. Right? What is an electric dipole? Define electric dipole moment, give its direction. This is also a important question. If this is only asked what is an electric dipole, can be 2 marks. If it is being asked define dipole moment, give its direction, it is a 3 marker. Dipole are two equal and opposite charges separated by a small distance, is known as electric dipole. Dipole moment. Electric dipole moment is the product of magnitude of one of the charges and the distance between them. It is a vector quantity. The direction of dipole moment is from negative to positive charge. So dipole moment is from negative to positive charge, and it is given by, the magnitude is given by q into the distance, that is q into 2a. Okay, so this is the dipole moment's definition. This is dipole moment, and this is the direction. Now, what is the unit of dipole moment? That can also be asked. Unit of dipole moment. So, if you see that this is Coulomb charge, this is distance meter. So, unit of dipole moment is Coulomb meter. Unit of dipole moment is Coulomb meter. In terms of dimension, Coulomb's dimension is current into time, and meter is L. So, it will be ATL, atal, or you can remember LAT, lat. Okay, both are dimension of the dipole moment. Both can be asked. Unit as well as dimension. Okay. Now, before I continue, I just wanted to share something very important with all of you, that if you don't want to pay anything, we have a free batch. Okay, and you all can join that free batch. Just give me some time. So you can go to our YouTube channel. Okay, you can go to our YouTube channel. Okay, search Diksha Karnataka. This is our YouTube channel, right? You can visit any one of our videos. For example, these are the videos that is currently live. You can visit here as well. Okay, and then you can scroll down, come here, click on the more button. Okay, and here you will get obviously Pariksha Vida. If you want to register for Pariksha Vida paid batch, obviously you can join it. But if you don't want to pay, you want some free batch, then you have to click on this join free second PUC course now. Click here. Okay, and you will be redirected to our home page. From here you have to click on buy now, and if you see that the price of the batch is 0, it's absolutely free of cost. You don't need to pay anything. Just click on the buy now. It will ask your mobile number, and once you have registered using the mobile number, you will get the free YouTube batch absolutely free of cost. Now what is the difference between here and YouTube? First of all, in YouTube a lot of videos are coming other than educational videos, other than teaching videos, and you might lost track of it, what is going on, what is happening. Here every academic videos are well listed. So if you go into the view section, okay, for physics, you click on this and you will see that all the lectures that is being done for our so far KCET as well as PUC, all the lectures will be available. You can check here. You can um, take the notes also. The notes will be available here. You can download the notes. You can access the videos anytime you want. You can watch it 2x speed as well, and you can ask Vedya will also be available, so you can ask any questions. Moreover, we will be providing some of the sample papers for your FA-1 practice as well. Okay, and if you click here, you will see that my tests, there will be some tests will be added very very soon, and you will get those as a sample paper as well. It is not there yet, but it will be added, and you will get access to that test, and you can check how much score you are doing in that paper as well. It will be a paper, you have to use it, right? I think it will be coming over here, resources section. Okay, and you will get that every notes, all the notes including this lectures note will be available in our course page only. Okay, the you can go and click any subjects, physics, chemistry, maths, biology, all subjects will be added over here, and all the lectures that we are doing on YouTube will be available through this, and it is absolutely free of cost. You don't have to pay anything. Just click on that link, okay, and register with your mobile number. If you are already registered, you don't need to do anything. You just need to log in using the OTP, and then you will get this access. Okay, so once it is done, just one time registration. Next time onwards, you just need to enter the mobile phone and OTP. If you have already logged in, you don't need to do that as well. But once it is done, you will get the entire batch absolutely free of cost. No need to pay anything extra, right? So this is what I want to say. This is absolutely free. You don't need to pay anything, anything, anything. Okay. Now let's continue with our discussion. Write 3 properties of electric field lines. So now we are discussing about electric field lines. Now in some colleges, if the college is preparing the paper, it can be asked as a 5-marker question as well, and then you should consider yourself lucky. But it never came as a 5-marker question in the board paper. But in unit 1, especially FA-1, if it is being done, if the paper is being set by the college, okay, there is a chance that this can be asked as a 5-marker question. Okay, so you need to remember at least 5 properties, not 3. Okay, 2-marker question is also possible, 3-marker question is definitely possible, 5-marker is also some cases will be there. Okay, so what are the 3 properties? So I have given 5 properties. You need to remember 3 of them is mandatory, 5 of them is optional, but I will request that you, if you study these 5 properties, you should be free from forever. Okay, for entire PUC syllabus till your board exams, these properties will be super important. This question is being asked repeatedly across different examinations. Okay, FA1, then midterm, pre-board, Same as Coulomb's law, this is also a super important question. Electric field lines may start from a positive charge and end at negative charge. Do not make these two a separate point. These two are same point. So I have seen students writing charge electric field line start from positive, it end at negative. Do not do that. Okay, it is basically single point. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Two electric field lines are never intersect each other. Electrostatic field lines do not form any closed loop. All these points are also important. For each and every point can be a MCQ question as well. So do not skip any of them. Electric field in free space decreases as we move in the direction of the electric field lines and vice versa. Okay, so electric field lines in free space decreases as you are moving. So that means if you are, so this is the electric field. Okay, if you are moving in this direction, okay, if you are moving in this direction, then the value decreases. Okay, so this is the direction where electric field decrease. Okay, and if you come from opposite side, it increases. Okay, so this is very interesting point. If you are moving in the direction of electric field, the value decreases. If you are moving in the opposite direction of electric field, the value increases. So vice versa means if you are moving in the opposite direction, it increases. That instead of writing the entire sentence, vice versa means opposite direction will result opposite value. Okay, that is the meaning of vice versa. Okay, some call it vice versa, whatever you are comfortable with. Now let's move into the 5 marker derivation from this chapter. Okay, let's see. Derive the expression for the electric field at a point on the axis of an electric dipole. Very important question. So here we have an electric dipole, say this let me use this. Okay, okay, so this is the dipole and we are trying to find electric field due to this dipole. So the dipole is, this is say plus q, this is say minus q, and we are trying to find electric field at some point p. We are trying to find electric field at some point p. Now in case of dipole, all the distances are measured from the center of the dipole. So the distance from here, center of the dipole to the point, is given by r. Because if you just take the distance from positive, the negative one will say why you are not measuring from me. If you take it from negative, the positive one will say why you are not measuring from me. So instead of that, okay, it says okay, not positive, not negative, let us measure the distances from the center. Okay, and the total distance of the dipole is 2a. So this is a, this is also a. Now how to find the electric field? To find electric field, due to if there is only one single charge, if there is only one single charge, say q, you are trying to find electric field at some point p, the distance is r, electric field is given by k q upon r square. Right, this is the formula, we already know that for a point charge electric field is k q upon r square. But here we do not have a point charge, we have two charges, one is positive, one is negative. Then how to calculate the electric field? So in that case we have to use superposition principle. What is superposition principle? Superposition principle is basically you have to apply the concept of electric field for individual charges at the point and then add them. So electric field due to positive you have to calculate, electric field due to negative you have to calculate, check their direction and then add them vectorially. That is very, very important. So for on the axis it is easy, okay. For equatorial plane it can be slightly tricky. So on the axis we know that this is positive charge. Electric field due to a positive charge is pointing away. No matter where you go, it is always pointing away. So suppose you are trying to find electric field over here. Electric field due to positive charge is always pointing away no matter where you go. So electric field due to this positive charge at P will point in this direction. Okay, whereas electric field due to the negative charge, which is located over here, electric field due to the negative charge will always point towards the charge. Remember, positive always away, negative always towards. So this is the electric field due to the negative charge. So this is say E minus and the other one is E plus. Okay. So what is the value of E plus? It is K Q upon distance square. So what is the distance from the positive charge to the point? So distance from the center is small r. So from here it will be r minus a. R is total. So if you minus a, you will get the distance from the positive charge. So it will be r minus a whole square. R minus a whole square. Right? So you just need to write it like this. Okay, so this is done. The next part is E minus. Now you have to calculate E minus. What is E minus? E minus is, again, now you do not consider the positive charge, only the negative charge you have to consider. For negative charge it is K. Now sign of the charge, whenever you are calculating electric field, do not consider the sign of the charge. Only direction of electric field is important. Do not put a negative sign when you are writing the electric field. Negative sign is only important to determine the direction, not the sign. So do not put negative in the equation. Never ever. Only for the determining the direction, the negative or positive is important. Otherwise, the sign of the charge is not important. Okay. Now let's see. For negative charge, what is the distance? K cube upon r square. That is the same formula. But what is the distance? The distance from the center is small r. Okay. From center up to center, it's small r. So if you add this small a, you will reach minus q. So it will be r plus a whole square. Okay. Now as we see that positive is away, negative is towards, that means they are in the opposite direction. These two electric fields are in opposite direction. So when we calculate the net electric field, it will be basically subtraction of one from another. Now which from which to what? Okay, for that you have to see that positive charge is closer to the point P. Positive charge is closer to the point P. So the electric field due to positive charge will be more. Electric field due to negative charge will be slightly less because it is slightly further away. So that means we have to calculate the electric field like this: E plus minus E minus. Okay, because E plus is bigger brother, E minus is smaller brother. So E plus minus E minus. Okay, so this is how you calculate the net electric field on the axis, of the dipole. So that's why we will mark it as axis. Okay, so this is the net electric field. Now what is left? Only you just need to put the values K Q upon R minus A whole square minus K Q upon R plus A whole square. Now it is pure mathematics. K and Q is common. We have 1 upon R minus A whole square minus 1 upon R plus A whole square. Just add them. So E axial will be K into Q, then we will be having R minus A whole square into R plus A whole square. That will be R minus A whole square into R plus A whole square. This is the LCM. Now R plus, I think R plus A will come over here, R minus A will come over here, right? 1 by say X plus 1 by Y. If you add them, what you do, you just do X into Y plus X, right? In case of minus, Y minus X. Same thing we are doing here as well. So the denominator is just multiplied and they are crisscrossing in the top. So it will be R plus A whole square minus R minus A whole square. Now, if you remember one simple formula, that is A plus B whole square minus A minus B whole square can be written in a one line, that is 4A into R. Okay, 4AB. 4AB equals to A plus B whole square minus A minus B whole square divided by R minus A whole square, R plus A whole square. So just take the whole square common, you will get R plus A into R minus A whole square. Okay, so what is this? A plus B into A minus B. So A plus B into A minus B is A square minus B square. So this becomes KQ 4AR divided by R square minus A square whole square. Now we will do a small approximation. What approximation? Just a second. I need to change the setting, I guess. Okay. I don't know what is happening. Let me change the background color. Just a second. Give me a thing. Yes. Done. Okay. Now, what we can do is, what was our expression for electric field on the axis? Electric field on the axis is given by KQ. We have 4AR divided by R square minus A square whole square. Now we have to do an approximation. The approximation is the dipole. The distance between the charges in a dipole is very small, because definition of dipole says that the distance between them is very, very small. So in that case, basically that means the we can write distance R is very, very larger than distance A. So what is the meaning of that? The meaning is, if R is very, very larger, say R is 1000, okay, and A is say 1. So if you do 1000 square minus 1 square, the results almost remain same. Okay, does not change by much, right? If this value is 1000, this value is 1. So if you do the math, it will be just 1 0 less actually. So it is almost same value, right? 999 or 1000, almost same value, right? So you don't need to do anything. So you can ignore this A. So for R very, very greater than A, okay, we can write electric field on the axis KQ upon 4AR divided by R square. Simply R square whole square. This whole square should also be there, right? So R square whole square. Now let's continue. KQ upon 4AR divided by R to the power 4 one of the r gets cancelled, and we are left with k 4aq by r cube. This is almost done. One small step is left, which is E axial will be equals to k 2aq into 2 divided by r cube. So what we have done, we have divided the 4aq term into 2 into 2aq. Right? Now why so? Because 2aq is the dipole moment of the dipole. 2aq is the dipole moment of the dipole. So we just need to put the, now we have to put the suits on. Okay, so normally so far the expression was in at home. Now it is going for a marriage. So you have to put the formal dress on, right? You cannot go in your home dress to a marriage. So this 1 by 4 pi epsilon naught is the marriage suit. So that has to be worn. And 2aq is our dipole moment. So it will be 2p upon r cube. Okay, so this is the expression for electric field on the axis of a dipole. Now, if you want to write this in a vector form, so if you go back here, if you see that the net electric field is in this direction, the dipole moment is from negative to positive. So, dipole moment and electric field both are in the same direction. So, if you write this thing in the vector form, it becomes E axial equals to 1 by 4 pi epsilon naught 2p vector upon r cube, right? This is the vector form. You can leave your answer at this stage. If you want, you can go into the vector form as well. Okay, so this is how you need to do the derivation. This is very important derivation from this chapter. You have to practice it 2-3 times. Otherwise, you will, if you are not practicing, you are thinking I will manage it in the exam hall. It will not going to happen. If you are not practicing it, you will not be able to do it. Okay, you do not have enough calculation practice. That is one major problem. Okay, if you have done it in the past also, at least once, practice it once, so that your memory is refreshed. Okay. Hi Anirudh, what are you trying to say? I don't understand. Yo Toto. I don't know what is the meaning of that. Derive the expression for electric field at a point on the equatorial plane of a dipole. This is also super duper important. Let's do that as well. Now here we have a dipole like this, and we are trying to find the electric field on its equatorial plane. Equatorial plane means this plane is called equatorial plane, which is basically dividing the dipole into two equal halves. If dipole is being divided into two equal halves, that is called equatorial plane. Okay, so this is my positive charge, this is my negative charge. Okay, now why I am doing why I am choosing the charges like this, this is only for the sake of drawings. Okay, you can take any positive or negative, does not matter, only for the sake of drawing I am choosing this. Okay, same thing was done in your textbook also. So now suppose I am trying to find the electric field at some point P. Okay, and then what we need to do, you need to join these points. Okay, and the distances are, this is r, this is also r, sorry. So as I mentioned, the distance is always measured from the center of the dipole, so this will be r. Okay, so this is say r dash, this is also be r dash. Equatorial plane means these angles are same, these two angles will be theta. Okay, this is an isosceles triangle, so these sides will be same and the angles will be same because it's an equatorial plane. This is a, this is also a. Now using Pythagoras theorem, you can calculate the value of r dash. R dash square equals to a square plus r square. So r dash is basically square root of r square plus a square. right? Pythagoras theorem, this is hypotenuse, this is 90 degrees, this is a, this is base, this is height. So you can calculate the hypotenuse value. Now this is done. Now if you see that both charges in this case are equidistant from the point P, this is also r dash, this is also r dash. That means magnitude wise, electric field due to the positive charge should be equals to electric field due to the negative charge as well. Magnitude wise, direction will be different, but magnitude will be same, and that magnitude, let us denote, say this is E, because charges are equidistant on the equatorial plane. So magnitude will be same, and that value we are saying E. And what will be the value of E? It will be simply KQ upon R dash whole square. For a single point charge, right, you can put the value of R dash square as well. It will be KQ upon R square plus A square. Square root was there. The square root is gone now because you have done a square here. So R square plus A square. This is the electric field due to both charges. Now we have to look into the direction. Now we have to look into the direction of the charges. Okay. So if you see that for positive charge, electric field will point away from, and from a negative charge, the electric field will point towards the negative charge. This is always true, right? For a negative charge, electric field will be towards the charge. For a positive charge, electric field will be away from the charge. Okay. Now, if you trying to find the addition of these two forces, how to do that? This is not simply one in the opposite direction. So you have to use some method to find it. For that, we will be using basic resolution of vector. We will be using basic resolution of vector. So if you consider the y component of individual charges, obviously both of them have same magnitude, so their y components must be same. Now if you are wondering why, because this angle will be theta, this angle will also be theta, okay, because this angle is similar angle with this theta, and this is opposite angle of this theta, okay. So that alternate angle, so this angle should be same, alternate angle, this angle should be same, similar angle, okay, and that's why these two angles will also be same. So if you take the sine theta component of that, you will get the y component. So this is also e sine theta, this is also e sine theta. So y components cancel each other. So Ey is 0. So y components cancel each other. Only the x component for individual charges are left. So what is the x component? So x component is actually the electric field on the equatorial plane. The x component is the electric field on the equatorial plane. Now how to do that? So here this is E, this is also E, this angle is theta, so this component will be E cos theta. So this will be E cos theta plus E cos theta. E cos theta due to this, E cos theta due to this. So both of them will be having cos theta components only. Again, this requires much more practice than the previous one. This is much trickier than the previous one. In the previous case, they are in the opposite direction. Simply addition or subtraction was done. But here, you have to take the component, resolution of vector. That means you have to take the components. So E cos theta plus E cos theta. So you get 2E cos theta. Okay, so E value is known. Now let us try to find the cos theta value. For cos theta, let us use this triangle. If you are using this triangle, again, some people have curly brown hair, turned permanently black. So cos theta is base by hypotenuse. So what is base over here? Base is A. Base is A. Hypotenuse is R dash. Hypotenuse is R dash. Or it will be A divided by R square plus A square to the power half. Square root can be written as power half. So that is cos theta. Now we will be using those values in our equation. Just substitute these values. E is k q upon r square plus a square. Cos theta is a divided by r square plus a square to the power half. Okay. Now simplify. So let me write it like this: q into k into q into 2a. So basically we have taken this 2a inside the bracket. Outside it will be r square plus a square to the power 3 by 2. Right, it will be to the power 3 by 2. Now again we will use the approximation, that is r is very large than a, so we can ignore this a square term. So electric field on the equatorial plane will become, now q into 2a is our dipole moment P, and in the division we have r square to the power 3 by 2. So r square to the power 3 by 2 means what? R square to the power 3 by 2 means what? R to the power 2 into 3 by 2. So 2 cancels, that is r cube. Okay, so that we will use here. So electric field on the equatorial plane becomes, again we have to give it the marriage dress. So 4 pi epsilon naught P upon r cube. Now this is not done yet. For equatorial plane, the vector form is very important. Now if you are trying to find the vector form, okay, remember that the dipole moment is from negative to positive, and for both charges it is from positive to negative. Okay, so electric field, the net electric field is in this direction, whereas the resultant electric field for dipole, it is in the opposite direction. So equatorial plane is given by, this is a small mistake, this is dipole moment. So dipole moment and electric field, they are in the opposite direction, so there will be a negative sign. And negative sign comes only when you are writing in terms of vector notation. Otherwise the negative sign will not come. Negative sign will only come in the vector notation. So remember, the negative sign is super important. So minus 1 upon 4 pi epsilon naught P upon r cube. Right? Now let's move on with the next derivation. Derive an expression for electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss's law. Now sometimes they might ask state Gauss's law and do this derivation. Both are okay. So what to do here? So first of all, we have to take an infinitely long straight wire. So this is a uniformly long straight wire. Okay, it has some charge in it. Some charge, say positive charge. And we are trying to find electric field due to this wire at some distance, say r. We are trying to find electric field due to this wire at some distance r. Okay, what to do? How to calculate it? What is given here? The line charge density is given. Line charge density means you take unit length of this wire and see how much charge is there. So that is the line charge density, and that is denoted by the symbol lambda. So if the length of the wire is 1 meter, whatever is charged there in that 1 meter, that is called line charge density. Okay, SI in SI unit. Okay. that is the line charge density. Now that is given in this question. Lambda is given, not the total charge. Now total charge does not make any sense also, because this is an infinitely long wire. This is an infinitely long wire. So what to do? We have to construct a Gaussian surface. We have to construct a Gaussian surface to solve it. So we have to construct a Gaussian surface, and here the Gaussian surface is a cylinder. So let me draw it. So Gaussian surface here is a cylindrical Gaussian surface, because a straight line have cylindrical symmetry. So this is a cylinder that we have to draw to show that this is our Gaussian surface. Okay, and say the length of this wire, this cylinder, is say L. Length of this cylinder, say L. Now electric field will passing through this cylinder will always be normal to the surface, each and every point. Okay, electric field passing through the cylinder will be normal to each and every point, and there will be no electric field through the top and bottom, because electric field lines has to be normal. So electric field line cannot be in this direction, because the line charge density is distributed like this. So positive charge means electric field is always will be away from. So this is the basic diagram for this derivation. Derivation, if there is a diagram required, you have to draw the diagram. Without diagram, derivation will not give you any marks. Without the diagram, derivation will not give you any single mark. So be careful about it. Okay. Now, so once you have completed the diagram, now let's look into the derivation part. Here, Gauss's law says that the electric flux coming out of a closed surface is always the charge enclosed divided by epsilon naught. Okay, the flux coming out of a closed surface is always charge enclosed by epsilon naught. Now here the closed surface can be imaginary. Closed surface, for example, here we have taken an imaginary surface, so Gaussian surface can be imaginary. But if it is a closed surface, the Gauss's law is valid even for an imaginary surface as well. So Gauss's law is valid for an imaginary surface as well. So here it's an imaginary surface, and Gauss's law is still valid for this imaginary surface. Okay, as long as it's a closed surface, and it is a cylinder closed from both sides, so it's a closed surface. So Gauss's law is valid. So this law is valid. Now how to do that? We know that flux is basically electric field into area, but here electric field is changing with the distance. So electric field needs to be written as E dot dA close integration Q enclosed by epsilon naught. Now few things that you have to determine: how to solve this integration and what is the charge enclosed. These two things we have to figure out, then the derivation is very easy. So we know that line charge density means for 1 meter wire, charge is lambda. For L meter wire, what will be the charge? Unitary method. For 1 meter, lambda. For L meter, what is the charge? Because this much charge is enclosed in the surface. So this much charge we have to calculate. So what is this much charge? This much charge is basically the length of the wire into the charge density. So charge enclosed is L into lambda. So this is done. Now let us figure out how we can solve this integration. To solve this integration, it is not difficult. Just you need to understand that because of symmetry. Symmetry means if you are standing over here or here or here or here, or from this side, or on the, this is three-dimensional figure, any point on the cylinder, because the wire is infinitely long, no matter where you are standing, as long as this distance r is fixed. Okay, as long as this distance r is fixed, no matter if you are on the right side, left side, front or back, electric field should be constant. Okay, electric field should be constant because of the symmetry. This is an axial symmetry. That's why Gauss's law is very helpful to determine electric field in case of symmetrical surfaces. Okay, even though it is applicable for any design, any surfaces, but we choose symmetrical surfaces so that we can make electric field constant. Now, similar to that of differentiation, when you do differentiation of a constant, the constant comes out of the differentiation, only the variable gets differentiated. Similarly, for integration also, the constant comes out of the integration, and you have to write one line: due to symmetry, E must be constant at each and every point on the cylinder, right? So that means it will come out of the integration, and therefore we can write the integration will be, the same equation can be written as E into integration dA equals to charge enclosed is what? Charge enclosed is L into lambda. So L into lambda divided by epsilon naught, right? So this E comes out of integration, only dA is left. Now charge enclosed is L into lambda divided by epsilon naught. So now we have to figure out what is this value of close integration dA. So close integration dA, that we have to figure out. Close integration means for a surface, if it is a close integration, it gives the total surface area. If it is a volume, it gives the total volume. Here it is area, so we don't need to consider anything else. So that will be total surface area of the curved surface. What is the curved surface area of a cylinder? The area of a curved surface is basically given by 2 pi RL. That is the surface area of a cylinder, curved surface area. We are not considering the flat surfaces because electric field is 0 there. So from there we can just write that this will be 2 pi R into L. So this is the total surface area of the curved surface of the cylinder, right? So just use that basic geometry. Now the physics is over. So L into lambda by epsilon naught, just need to simplify this. So electric field E becomes 1 by 2 pi RL into L into lambda upon epsilon naught. So obviously L cancels, and we get 1 by 2 pi epsilon naught lambda upon R. So we just exchange the R and epsilon naught. Now this is not the this is the final derivation, final answer, but I like to write it slightly differently, which is 1 by 4 pi epsilon naught 2 lambda upon R. Okay, why I write it like this? Because 1 by 4 pi epsilon naught is standard constant, 9 into 10 to the power of 9, and this might be very helpful for solving some MCQ numericals for KCET. That's why I ask my student to remember this formula. Now, very interestingly, if you see here, electric field is inversely proportional to the distance. It is not square of the distance, not cube of the distance, only inversely proportional to the distance. So for a single charge, point charge, it is 1 upon r square. For a dipole, it is 1 upon r cube. And for a line charge, it is 1 upon r. Okay. Now let's solve some numerical questions. 2-point charges of 4 nanocoulomb and 8 nanocoulomb are placed at the points A and B respectively, separated by a distance of 0.2 meter in air. Find the magnitude of the resultant electric field at midpoint O of the line joining A and B. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is replaced by another 8 nanocoulomb? So let's see. 2-point charges. In case of numericals also, draw the diagram for better understanding and solving the question effectively. That is a very good method. Okay, so 2 point charges plus 4 plus 8, both are nanocoulomb, I'm not writing that, are placed at the points A and B respectively. So this is A, this is B. Okay, they are separated by a distance 0.2 meter in air. The distance between them is 0.2 meter. Okay, find the magnitude of the resultant electric field at O. So O is the midpoint. O is the midpoint. You have to find the resultant electric field at this midpoint O. Okay. Now this is the second part. Second part we will come later. First, let us solve the first part. Okay. So how to calculate the electric field due to this combination at the midpoint O? So obviously we have to calculate the electric field due to the first charge, and then we have to find the electric field due to the second charge, find their direction, and based on that basically add them or subtract them. Okay, I am writing add, but it can be subtraction as well based on their direction. So what is the electric field due to EA? Electric field due to the charge on A is given by K QA upon R square. So this distance is R, this is also R. Okay, both distances are same. Midpoint means distances are same. Now it is given that if you add both distances you get this distance, so R plus R should be equals to 0.2. So 2R equals to 0.2 or R equals to 0.1 meter. So this is the distance that we need to consider. This is the electric field due to the first charge QA. What about the electric field due to the second charge EB? It will be K QB upon R square, same distance. Now let us see whether they will be added or subtracted based on their direction. So electric field due to the A is positive charge. Positive charge means electric field will be away from. Just make it a habit. Positive charge, electric field away from. Negative charge, electric field towards. So this is a positive charge also. So this will also be away from EB. So EB and EA both are in the opposite direction. That means we have to find the subtraction. Okay, now from which to which subtract? So if you see that B value is 8, A value is 4, so it will be EB minus EA. So we just need to do EB minus EA. That will be our net electric field. This will be our net electric field. So just put the values K QB upon R square minus K QA upon R square. I'm not putting the values, okay, because this way it will be much easier to simplify. K upon R square QB minus QA. Now we will put the values and calculate the answer. So the net electric field is given by K. K is 9 into 10 to the power of 9. Standard value. R square. R is 10.1 meter. 0.1 meter means 10 to the power of minus 1 meter. We will try to convert it in 10 to the power value. That will be much easier. R square means 10 to the power of minus 1 whole square into QB minus QA. QB is 8. QA is 4. Now here most of the students make mistakes. They forget that they are in nanocoulomb unit. They are in nanocoulomb unit, and it is very normal for most of you to ignore the nanocoulomb completely. So you should not do that. You have to use the nanocoulomb as well. So nanocoulomb means 10 to the power of minus 9. Do not ignore it. Make sure you understand the problem and put the 10 to the power 9 minus 9 as well. So 10 to the power plus 9, 10 to the power minus 9 cancels. What else? We have 9 into 8 minus 4 is 4 divided by 10 to the power of minus 2. 10 minus 1 whole square. Minus 1 whole square is minus 2. So it will be 36 into 10 to the power of 2. That is 3600 Newton per Coulomb. This is the net electric field. So first part is done. Now let us look into the second part. What will be the magnitude of resultant electric field at O if 4 nanocoulomb is replaced by 8 nanocoulomb? So if you replace this 4 nanocoulomb by another 8 nanocoulomb, what will be the net electric field? So in that case, net electric field will be uh, K upon R square 8 minus 8 into 10 to the power of 9 minus 9. That means this will be 0. So in that case, net electric field will be 0. So if you are solving it like this, you don't need to do anything else. You just show that mathematically electric field is coming out to be 0. So if you replace 4 nanocoulomb with another 8 nanocoulomb, net electric field will be 0. Now let's move on. 2-point charges QA equals to 5 microcoulomb and QB minus 5 microcoulomb are located A and B separated by the pointometer in vacuum. Almost same question. What is the electric field at the midpoint of the line joining the two charges? If a negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the test charge? Almost same, but there are differences. First of all, the charges are equal but opposite in sign. So here we have two charges. A and B. Okay, so this is plus 5 microcoulomb. This is minus 5 microcoulomb. We are trying to find the electric field at the midpoint O. So total distance is 0.2. So this is R, this will also be R, and same logic, R will be 0.1 meter. That is 10 to the power of minus 1 meter. Okay, everything is explained in the previous problem. That's why I'm not explaining why it is so. But you have to show it. In the problem, you have to show it. Now, what is the electric field due to A here? Electric field due to A is K QA upon R square. Formula wise, everything is same. Slight difference in the concept. Okay, QA, QB values are same. Now let us find the direction, whether they will be added or subtracted. That step is very important. So if you see that A is a positive charge. So positive charge means electric field due to EA will be away. Okay. Now B is on the other hand is a negative charge. So B is on the other hand negative charge means EB should also be towards. For negative charge, electric field is towards. For positive charge, electric field is away from. So in this particular case, both the electric fields are in the same direction. So the net electric field will basically be EA plus EB. Okay, that means K by R square is common, QA plus QB. Okay, but here you will only consider the magnitude of the charge. Remember, even though the charge is negative, you will only consider the magnitude of the charge. Never consider the sign of the charge. Remember, for electric field, sign of the charge is not important. Only the direction is important. That is super duper important point to remember. Okay, so now K value is 9 into 10 to the power of 9. R square is 10 to the power of minus 1 whole square. QA is 5 microcoulomb. QB is also 5 microcoulomb. And micro means 10 to the power minus 6. Okay, now let's simplify. You will get 9 into 10 to the power of 9 minus 6 is 3 divided by 10 to the power of minus 2 into 10. 5 plus 5, 10. Now it will be coming out to be 9 into 10 to the power of 5, 6. So 9 into 10 to the power of 6 Newton per Coulomb is the force acting on, the net electric field on the central point or midpoint. So this is done. This is part A done. Next part. This is part A answer. If a negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the test charge? Force experienced by a negative charge will be Q into electric field. Q into electric field. That is the simple formula that you need to apply. Okay, the charge is 2 nanocoulomb. Nanocoulomb means 10 to the power of minus 9. And net electric field is 9 into 10 to the power of 6. So it will be 18 into 10 to the power of minus 3 Newton. 18 into 10 to the power of minus 3 Newton force will be applicable. Units are also super important whenever you are solving any numerical question. For electric field, the unit is Newton per Coulomb. Okay, and for force, it is Newton. No matter whatever question you are solving, make sure your final answer always contains unit. It is not necessary to maintain throughout the question, but it is very important for you to remember that final answer should always contain units. Without that, marks will be deducted. A positively charged spherical conductor. I have one more from this chapter. Total 30 questions from this chapter. A positively charged spherical conductor of radius 0.1 meter produces an electric field of 1.8 into 10 to the power of 3 Newton per Coulomb. At a point P, distance 0.2 meter from its center, calculate the magnitude of the charge present on the spherical conductor. Also, find the magnitude of the new charge produced the same spherical conductor if 5 into 10 to the power of 10 extra electrons are removed from it. Interesting question. So, positively charged spherical conductor, radius given 0.1 meter, produces an electric field of 1.8 into 10 to the power of 3 Newton per Coulomb at a distance 0.2 meter. So, it is a spherical conductor. So, electric field due to a spherical conductor at a distance r for distances greater than r. So, if this r is greater than r, electric field due to the spherical conductor is given by k q upon r square. Same formula as a point charge. Only difference is inside the spherical conductor electric field is 0. Outside the spherical conductor it is same formula as a point charge. So the charge of the spherical conductor, if it is q, then we can use the same formula, and we can say that electric field is given here. In this particular problem, electric field is given as 1.8 into 10 to the power 3 Newton per Coulomb. Okay, the distance here is given 0.2 meter, that is 2 into 10 to the power of minus 1 meter. Okay, and they are basically asking what is the value of q, what is the magnitude of the charge. So let's see. So electric field is 1 point. So now we are just replacing these values in this equation. 1.8 into 10 to the power of 3 equals to k is 9 into 10 to the power of 9, right? K is 10 to the power 9. Q value we do not know, divided by r square. R square is 2 into 10 to the power minus 1 whole square. Okay, so Q will be equals to 1.8 into 10 to the power of 3 into 2 into 10 to the power of minus 1 whole square divided by 9 into 10 to the power of 9. Right, just cross multiplied, we have to found the value of q. So it will be, so 9 into 1.8 is 0.2. So 0.2 into 10 to the power of 3 into 4 into 10 to the power of minus 2 divided by 10 to the power of minus 10 to the power of 9. So it will become 10 to the power of minus 9. So the answer will come in nanometer. So that's why we are trying to solve it like this. So if you see, it will be 0.8 into 8. It will be 8 into 10 to the power of minus 9 Coulomb or 8 nano Coulomb. So the answer is 8 nanocoulomb. Just do calculation very quietly. You don't require a calculator to solve this also. If you solve it very quietly, you should be able to answer it. Now, next part is also find the magnitude of the new charge produced on the same spherical conductor if 10 to the power of 5 into 10 to the power of 10 extra electrons are removed. So basically this is the old charge. This is the old charge, say Q. Now we have to find the extra charge. If you find the extra charge, then the new charge will be basically the old charge plus the extra charge. Okay, so extra charge you have to find. How to find the extra charge? Basically, quantization principle, charge is n into E, number of electrons are given, that is 5 into 10 to the power of 10, and charge of an electron is 1.6 into 10 to the power of minus 19 Coulomb. So it will be 5 into 1.6 is 8, 8 into 10 to the power of minus 9 Coulomb, that is 8 nano Coulomb. So what is the net charge? The new charge will be the old charge plus the extra charge. So it will be 9 plus, sorry, not 9, 8 plus 8 nano Coulomb, that is 16 nano Coulomb. So the answer to this question part, this is the answer to the part A, this is the answer to the part B. Okay. So every question generally will have two parts. There will be not only one single part. If you solve one part, generally some marks will not be there. Okay, so you have to solve both parts. Very, very careful about it. Next, this is the last question for this chapter. We have one more chapter to do, so don't go anywhere. A uniformly charged spherical shell of radius 10 centimeter has a surface charge density of 16 microcoulomb per meter square. Find the electric field due to the shell at a distance of 10 centimeter from the center of the shell, 5 centimeter from the center of the shell. So uniformly charged spherical shell. This question is from your 2025 PU final exam. 2025 PU final exam, this question was asked. Okay, so charge density is given. Charge density is given. Okay, radius is given. Radius of the sphere is 10 centimeter. Okay, which is 10 into 10 to the power of minus 2 meters. That is 10 to the power of minus 1 meter. This is the radius. Okay. Now the charge density is given 16 microcoulomb per meter square. This is surface charge density. So what is the total charge? So this is the shell. Shell means obviously inside part is hollow like a football. Okay, inside part is hollow, only outer part is strong enough. So some charges are there in this shell. Okay, so how to find? First step is to calculate the total charge. First step is to calculate the total charge, and secondly, we know that electric field due to a conductor or a spherical shell outside the shell obeys the same formula as a point charge, that is kq upon r square, and inside the electric field, inside the shell, electric field is 0. So if you see the second part, 5 centimeter from the center, that is it's an inside point, so electric field will be 0. 20 centimeter will be outside point, so it will be basically kq by r square. So same formula. Easy question, but can be tricky if you don't know how to calculate the total charge. Total charge total charge in a surface of a spherical shell is basically the surface charge density into total surface area. Surface charge density into total surface area. So charge density is 16 microcoulomb. Micro means 16 into 10 to the power of minus 6. What is the area of a sphere? Area of a sphere is 4 pi r cube. Area of a sphere is 4 pi r cube. So sorry, not pi r cube. Sorry. 4 pi r square. Okay. So just put the value 16 into 10 to the power of minus 6 into 4 into 3.14 into 10 to the power of minus 1 whole square. So it will come out to be 64 into 3.14 into 10 to the power of minus 8. This is the charge. Okay, let me calculate once. So just let me find the calculator. Yes. So it will be 64 into 3.14. It will be 200.96, approximately very close to 200 into 10 to the power of minus 8. So it will be 2 into 10 to the power of minus 6. So the charge enclosed by, or charge, total charge on the surface of the spherical shell is 2 microcoulomb. Okay, but they don't ask you to find the total charge. It is a part of the problem itself. Okay, even though they did not ask, you have to solve it. Now next part is the electric field. So now we are solving the electric field. Electric field is k q upon r square. Now here r is given 20 centimeter. Do not confuse with the radius. Here it is 20 centimeter, that is 20 into 10 to the power of minus 2 meter, or 2 into 10 to the power of minus 1 meter. We will use this in this equation. Now k is 9 into 10 to the power of 9. Charge is 2 into 10 to the power of minus 6. And the distance is 2 into 10 to the power of minus 1 whole square. So it will be 9 into 2 into 10 to the power 3 divided by 4 into 10 to the power minus 2. 2 2s are 4, 2 9s are 4.5. So it will be 4.5 into 10 to the power of 5. Okay, and it is Newton per Coulomb. Okay, so this will be inside, outside the sphere, outside the shell. Now for the point B, the distance is 5 centimeter. R is 5 centimeter, which is less than the radius of the spherical shell, and in that case electric field will be 0. So this is say 5, this is 20. Okay, so electric field inside the shell will be 0. This is 5 centimeter, this is 20 centimeter. Okay, electric field inside the spherical shell will be 0. So part B, you don't need to do anything, you just get 1 mark for writing electric field is 0. If you don't write it, you lose 1 mark. Right? Now, this is the end of this chapter. Before starting the next chapter, I will take a 10-minute small break. So give me some time. Yes. Where is the timer? Yes. So I will take a small 10 minutes break and then I will be coming back. Okay. Yes, I am back now. Let's continue with electrostatic potential and capacitance with more energy, right? Let's start. Okay, let's start quickly. Angle between equipotential surface and electric field is. So if there is an equipotential surface like this, and if there is an electric field like this, the angle is basically 90 degree. Angle between equipotential surface and electric field is always 90 degrees. Okay. Now next, the electric potential due to a negative point charge at a distance r is positive, and it varies as 1 by r, positive and varies as 1 by r square, um, negative and varies as 1 upon r square, negative and varies as 1 upon r. So electric potential due to a negative point charge. So what is the formula for electric potential? It is kq upon r, almost same as electric field. Only thing is it is only 1 upon r, right? So electric potential due to a point charge is kq upon r. So if the charge is negative, this is a scalar quantity. So if the charge is negative, potential will be negative. So if this is negative, the potential will also be negative, and obviously it is proportional to 1 upon r. So negative, and it is proportional to 1 upon r only. Let's move on. Values of electric field E and electric potential V at any point on the equatorial plane of an electric dipole are such that, so values of electric field E and potential V on any point on an equatorial plane of a dipole. So for a dipole, so this is the dipole. Suppose this is say positive, this is negative. On the equatorial plane, electric field, we already seen that it is proportional to 1 upon r square, r cube, right? But electric potential on the equatorial plane is 0. Electric potential on the equatorial plane is 0. Electric field is not 0, but electric potential is 0. So E not equals to 0, V is equals to 0. Very interesting, important question. Do mark it. Okay. Similar questions might come in your FA-1 as well. Which of the following is the unit of capacitance? Unit of capacitance is farad, nanofarad, picofarad, etc. Here option is given farad, so we will mark farad. No problem. Spherical conductor of radius capital R is carrying a charge of plus Q. The ratio of the electric potentials corresponding to a point on the surface of the conductor and at a point at a distance 2r from the center of the conductor are in the ratio. Okay. So on the surface of the conductor, electric potential is given by kq upon r. Okay, and at a distance 2r from the center of the distance, it is given by, say this is V1, this is V2. kq upon 2r. Simple formula, nothing, no rocket science over here. So just apply the basic formula for potential. Very simple. Electric potential is constant from center till the surface, and as you are going out, it decreases with 1 upon r, right? So so what is the ratio? V2 upon V1 is kq upon 2r by kq upon r. So it will be 1 by 2, that is 1 is to 2. So it will be 1 is to 2, that is the ratio due to first order of the question is important. So any ratio based questions, check, make sure that order is correct. So first is ratio on the electric potential corresponding to a point on the surface is given first. Second is given at a distance 2r. So order is super important. So order is super important. So I think I make a mistake. So first will be V1 by V2. V1 is kq upon r, and V2 is kq upon 2r. So it will be 2 upon 1. So it will be 2 is to 1. So correct answer will be option B, not option A. So I am making a mistake. You should not make the same mistake in your exam as well. So make sure the order with which the ratio is being asked, you are doing it like that only. Now, if you want to get a free batch, absolutely free of cost, without paying anything else, then what you can do is go into the description section of our YouTube live right now, which is going on here. You just go to the description section, click read more, and once you reach over here, just click on the join free second PUC course. Click on this link, and this link will open, and then you have to click on buy now. Once you click on buy now, it is 0 rupee. You don't have to pay anything else. Okay, even I have registered in this course. So once you log into this page, okay, it will be visible to you. You just click on continue. All physics, chemistry, maths, biology, all subjects, whatever lectures that we are doing on YouTube, here it is available in a structured way, exactly the way you are supposed to learn. Okay, exactly the way you are supposed to learn. You can go into the course itself. You can see some assignments will be given over time. So don't worry, the assignments will be, if everything will be absolutely free of cost. Assignments will be given on time. Some free mock test paper will also be given to you absolutely free of cost. You just go here, click on this, and all the lectures will be here. Okay, you just need to click on play, and the videos will be played automatically. You don't need to do anything. You just play all the lectures the way it should have been done. All the latest lectures will be available along with one shots. Then the YouTube Ace series that is going on, but it will be much more structured. You will not have to look for anywhere else. Sir, I need to check the lecture that you have done 2 weeks back. I am not able to look for it. Don't worry. You just come here. You just look for the session. It will be automatically be added. This live session will also be automatically be added in this page only. So this is a single page that you need to consider. All subjects will be available. Also the notes of the lectures will also be added in this session. So don't need to worry anything about it. Right now, so this is our course page. This is absolutely free of cost. You don't need to pay anything for joining this batch. Right now, let us continue with our session 6. Question number 6. The dimension of electric polarization is given by. What is electric polarization? So electric polarization is given by, so electric polarization is denoted by capital P. Okay, it is the total polarization of the crystal divided by its volume. Polarization of the crystal divided by its volume, that is the electric polarization. Okay, dimension of electric polarization, this is dipole moment divided by total volume. So what is the dipole moment? If you remember, I told you the dipole moment few moments back. The dimension of dipole moment is LAT. LAT, lat, or sometimes I remember it as atal, ATL, okay, or LAT, lat for you. Just a second, give me a second. Okay, okay. So now, so dipole moment per unit volume is called the electric polarization. Now, if you want to find the electric polarization, basically you have to divide it by the volume. What is the volume's dimension? Volume's dimension is L cube. Okay, so LAT divided by L cube. So it will be turning out to be L to the power of minus 2 A into T. So L to the power of minus 2 A into T, that is the dimension of electric polarization. This is a very different quantity than dipole moment. Electric polarization is when you apply an external electric field, the dielectric medium, it develops a dipole moment, and based on that external electric field, the polarization of the medium can be calculated, and that is called electric polarization. Okay, so electric polarization's dimension is L to the power of minus 2 A into T. Next question. The electric potential at the surface of a charged spherical shell of radius 10 centimeter is 20 volt. The electric potential at the center of the shell is. So, electric potential at the surface is 20 volt. So, what is the electric potential at the center? Don't worry, electric potential inside the shell is constant, so you don't need to do any mathematics over here. So, if 20 volt given over here, 20 volt should be here as well. So, no need to change anything, it will be 20 volt only. Do not mark 0 thinking it is center, it is inside. Potential is constant, electric field is 0. Potential is constant, electric field is 0, and that is from the center till the surface. Onwards, surface onwards, it changes. Now, next is the electric field at a point which is very close to the surface of the charged conductor with the surface charge density sigma. So, if you have a charged conductor and you are trying to find the electric potential on near the charged conductor, electric field near the charged conductor, it comes out to be sigma upon epsilon naught. This is the property of a conductor. Okay, few points that you need to remember about conductor. It is sigma upon epsilon naught. So, it will be option B, sigma upon epsilon naught. For a charged plate, if it is a single plate, okay, infinitely long or very close to a charged plate, it is sigma upon 2 epsilon naught. Don't be confused. For a charged plate surface, this is sigma upon 2 epsilon naught. This is a volume. Okay, this is a surface, this is a volume. Okay, so for a volume, this is conductor, and this is only applicable for conductor only, because conductors do not have any electric field inside. For a conductor volume, the electric field near the conductor is sigma upon epsilon naught, but for a surface, it is sigma upon 2 epsilon naught. Both looks very similar, but there are slight difference between them. Next, the energy density between the plates of a charged capacitor is given by. So, energy density between the plates of a charged capacitor is given by energy density, by the way, not energy. Energy density between the charged plate is given by U equals to small u half epsilon naught E square. Okay, so if you see that, this is the correct answer. This is the correct answer. Do not fall for half CV square or half QB. It is half epsilon naught E square. CV square is total energy. Energy density is given by total energy by volume. Okay, volume. Okay, so that is small difference here. Now, next question. An electric dipole is placed in a uniform electric field. The dipole moment makes an angle theta with the electric field. For what angle theta is the potential energy of the dipole is maximum? So, when you keep a dipole in an external electric field, it experiences a torque and it also has a potential energy. So, what is the formula for potential energy? Formula for potential energy is minus PE cos theta. The expression for potential energy is minus PE cos theta. Now, when this value will be maximum? The value will be maximum when cos theta's value is minimum. Now, cos theta's value minimum is not 0, it is theta equals to 180 degrees. At theta equals to 180 degrees, cos theta becomes minus 1. So, the potential energy maximum value becomes plus PE. Okay, positive value is bigger than negative value. So, the maximum value of the dipole moment will be when theta, potential energy will be when theta is 180 degrees. Okay, minimum value, again, minimum value is still not 90 degrees. 0 is not minimum, negative is more smaller than that. So, minimum potential energy minimum. So, for maximum value, theta is 180 degrees. For minimum potential energy, the energy will be minus PE, that is theta equals to 0 degrees. So, maximum it will be theta 180 degrees, minimum it will be theta 0 degrees. Both are important. Now let's move on with some fill in the blanks. A molecule possessing permanent dipole moment is called dash molecule. It is called polar molecules. Let's see if the options are given or not. Non-conducting. Non-conducting molecule does not make any sense. Nanofarad molecule does not make any sense. Distance molecule does not make any sense. Polar increases, decreases. So obviously polar is the answer for this. So permanent dipole moment is called polar. If they do not have permanent dipole moment, they are called non-polar. The potential due to a dipole, depends on dash. So potential due to a dipole depends on non-conducting. Distance could be an answer. Increases, decreases. Obviously, non-conducting is not possible. Increases, decreases is also not possible. So definitely it will be distance. Okay, so potential due to a dipole depends on its distance. And in fact, potential due to a dipole is proportional to 1 upon r square. Electric field due to a dipole 1 upon r cube. Potential due to a dipole 1 upon r square. Okay. As the distance between the plates of a capacitor is increased, the capacitance. So capacitance is inversely proportional to the distance between the plates. So that means if you increase the distance, capacitance decreases. So this is very careful. Do not write increases, decreases. Increases, decreases both could be possible language wise, but theory wise only decreases is the correct answer, not increases. Next, capacitance is measured in. So only one unit of capacitance is given here, nanofarad. So we will write that nanofarad here. Capacitance is measured in nanofarad. Okay. Next, dielectrics are non-conducting substances. So in the given options, only non-conducting is left. So it will be non-substances. Okay. Now let's move into 2-3 marker question. 2 markers, starting with 2 markers. What is an equipotential surface? What will be the shape of the equipotential surfaces corresponding to a single point charge? Okay, any surface which has the same electric field, same electric potential at every point is called an equipotential surface. So if you consider a surface, if each and every point have same potential, then that surface is called equipotential surface. Okay. The shape of equipotential surface is spherical for a single point charge. If the charge is single point charge, it will be spherical. Okay. If the charge is line charge, equipotential surface will be cylindrical. Okay. Remember this. Next, on what factor does the capacitance of a parallel plate capacitor depends? So we know that capacitance of a parallel plate capacitor is given by C is equal to A epsilon naught by D, where C is capacitance, A is area of the plates, and D is the distance between the plates, and epsilon naught is the free space permittivity. Permittivity. Remember, permittivity. Okay, some maybe you are confusing with the spelling. Remember, per, how to write permittivity? Per MITTI mittivity. Okay, this is the spelling of permittivity. So now from this expression, capacitance is directly proportional to A. capacitance is inversely proportional to D. So this is the thing. If you are using this method, you have to explain the diagrams, or you can directly use the equation and then write in terms of sentences also. Capacitance is directly proportional to area of the plates. Capacitance is inversely proportional to the distance between the plates. So that is also a way of writing. Or if you are using this symbolical explanation, then you have to explain what are all the terms. That is super important to remember. If you are just writing like this, the teacher might deduct 1 mark because you have not explained the terms. Okay, so either write in full sentence, or if you are using this, you explain the terms. Now next, write two properties of equipotential surface. This can be asked two properties, this can be asked three properties as well. Okay, no work is done moving a test charge over an equipotential surface. Okay, electric field is always normal to the equipotential surface at every point. No two equipotential surfaces intersect each other. This one is almost similar to that of electric field. No two electric field lines cross each other. Similar to that, no two equipotential surfaces can intersect each other. Okay, now let's move on. Obtain the expression for the effective capacitance of two capacitors connected in parallel. Now we have to find the effective capacitance of two capacitors connected in parallel. So here we have two capacitors connected in parallel. Parallel combination means basically it looks like this. Both of them are individually connected to the same battery, then it is called parallel combination. Okay, this is parallel combination. So say this one has a capacitance of C1, this one has a capacitance of C2. Now what is the net capacitance, or the total capacitance of this system? So how to do that? So for that, say the voltage that we are applying is V. Now as I mentioned, in parallel combination, both capacitors have same voltage. Voltage remains constant. So voltage between the capacitor is same, that is V. Okay, now what is the meaning of equivalent capacitance? Equivalent capacitance means we replace this two capacitor system with only one single capacitor having the equivalent effect. Nothing changes in the circuit. Only thing that changes is that two capacitor becomes one capacitor. Okay, so if we replace this two capacitor with one capacitor, so that everything in the circuit remains same, that is called an equivalent capacitor, right? So this is the voltage, so everything remains same. So if suppose what is the charge stored in the capacitor, say this one is storing charge Q1, this one is storing a charge Q2. So what is the total charge stored? Total charge stored over here is Q1 plus Q2, right? So in the equivalent capacitance, the charge stored should be Q1 plus Q2. Okay, so equivalent capacitor should store equal amount of charge that is being stored inside the individual capacitors. Now we know that for a given capacitor, Q is equal to CV. Q is equal to CV for capacitor number 1. For capacitor number 1, this is our number 1 capacitor, this is our number 2 capacitor. So capacitor number 1, we can write Q1 equals to C1 into V. V is constant. For capacitor number 2, Q2 equals to C2 into V. And for our equivalent capacitance, say the total charge stored here is Q. Okay, then Q is equals to C equivalent into V. The voltage remains same for equivalent capacitor as well. Okay, now what is this Q? That Q is Q1 plus Q2. That is equals to C equivalent into V. Now we just need to put these values over here. So this is equation 1, this is equation 2, this is my equation 3. So we just need to put the values and simplify. So what is the value of Q1? Q1 is C1V. What is Q2? Q2 is C2V. And on our right hand side, we have C equivalent into V. So now let's take V common. C1 plus C2 equals to C equivalent into V. Okay, obviously V cancels and we get C equivalent equals to C1 plus C2. Doing this simple derivation can give you 3 marks. Very common, mostly asked throughout the year. Series and parallel both are important. We started off with the parallel one. Now let's do the series one. Obtain the expression for effective capacitance of two capacitors connected in series. So here we have two capacitors. Series one is slightly tricky. Here we have a capacitor, voltage V. This one has a capacitance C1, this one has a capacitance C2. Now if you replace both of them by a single capacitor, you will get the equivalent circuit. Equivalent circuit for series and parallel remains same because we are only having one single capacitor. Okay, and everything else in the circuit remains same. Now in case of series combination, because it is an isolated system, charge should be constant. So whatever charge is passing through this side, the same charge should pass through this also, same charge should pass through this also. So the both capacitors should have the same charge, but because they are connected in series, the voltage drop across them should be different. Voltage drop across them should be different. So same in case of equivalent circuit also, the charge should be same, voltage is V as usual. Okay, now for capacitor number 1, we can write Q equals to C1 V1. For capacitor number 2, we can write Q equals to C2 V2. The same formula, Q is equal to CV. Only in parallel case, voltage constant. In series case, charge constant. That is the basic difference. Otherwise, everything is same. So Q is equal to C1 V1 and Q is equal to C2 V2. And for equivalent case, it will be Q equals to C equivalent into V. Now we know that voltages are distributed from this source voltage. That means the total voltage should be equals to V1 plus V2. So from this equation we have to calculate V1. So V1 equals to Q upon C1. From this V2 equals to Q upon C2. Okay, and from this V equals to Q upon C equivalent. Right? Now we just need to substitute that in this value. So Q upon C equivalent equals to Q upon C1 plus Q upon C2. Okay, now if you take Q common, you will get 1 upon C equivalent equals to 1 by C1 plus 1 by C2, or 1 by C equivalent equals to C1 C2 C1 plus C2, or C equivalent equals to C1 C2 by C1. This is specifically for two capacitors, and you can leave your answer over here as well. This formula is important for numerical questions, but you can leave your answer here as well. Okay, series parallel done. So remember, in series the total charge remains constant. In parallel, the voltage remains constant. Otherwise, same process is same, application wise it is different. Give 3 results of electrostatics of conductors. Okay, inside a conductor, electrostatic field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Okay, the interior of a conductor can have no excess charge in the static situation. They are very standard. You can add the electrostatic shielding also, but that is slightly longer and will require more explanation. That's why I have skipped that. Okay, next is, this is also super duper important derivation. before starting that, let me have some water. Derive the relation between electric field, electric potential due to a point charge. So relationship between electric field and electric potential due to a point charge. So for that you have to draw a diagram like this. Now I am not super good in drawing a diagram, so I have skipped it. Now if you can't draw it, you can draw simple plane like this, one plane, another plane, okay, and you can show this is the field. Okay, so you don't need to draw it like this the artistic way. You can simply draw one plane like this, then the second plane like this, okay, and you say this is has a potential V, the top one has uh, V plus dV. I use dV, you can use delta V, whatever you like. Okay, then you draw an arrow, say this is the direction of electric field. Okay, now this is a charge q that you want to carry from this point to this point. This distance is dx. What is the work done? Basically what we have to do here, uh, we have to find the work done in two different methods, and then we compare those two work done. That is the only process that this can be solved. So first of all, when we are moving an electric charge in an electric field, say from point A to point B, what is the work done? The work done is given by, in terms of potential, work done to move a charge, test charge, say the test charge value is Q. Okay, we are moving a test charge, say Q, from point A to B. Okay, the distance between them, let me write it simply dx. Okay, and the difference in potential is dV. Okay, now we are moving a test charge from A to B. Okay, from A to B, A to P. Okay, the distance between them is dx. This one is kept at potential V, the top one is kept at potential V plus dV. What is the work done? So work done is basically difference in the potential in the way final minus initial into the charge. Work done is difference in potential into the charge. So here the work done in method 1. So first is method 1. So the work done is given by the difference in potential, that is final potential. What is final potential? You are moving from A to P. So final potential is V plus dV minus initial potential. Initial potential is V into the charge. This is the work done's formula in terms of potential. So you get Q into dV. If you have followed my theory lectures, there I have discussed it multiple times. So work done is given by Q into dV. So work done for method 1 is done. Now work done in the method 2 we have to calculate. So method 2, what is method 2? Now we have to find what is the force acting on this charge. Okay, and we have to apply an external force in the opposite direction of that charge. So there is a force. This is the positive charge. Electric field is pointing in this direction. So we have to apply the electric forces in that upward direction. So we have to apply an external force. So the external force must be opposite to that of the internal electric force. What is electric force acting on a charge? Electric force acting on a charge is given by Q into E. Electric force acting on a charge is given by Q into E. So that is minus QE. So this much force we have to apply on the charge to make it move. Now if I am applying a force, if the distance is small, we can assume this force is constant. So what is the work done? Work done definition according to force is applied force into the displacement. Applied force into the displacement is our work done. So that means it will be Q into minus minus q into E into dx. Minus q into E into dx. Now both work done must be same. So work done here is q into dv, and work done here is minus q into E into dx. So obviously q cannot be 0, so q is cancelled. So we get dv equals to minus E dx, or E equals to minus dv upon dx. E equals to minus dv upon dx. So this is the relationship between electric field and electric potential. Remember, the minus sign indicates that electric field is decreasing. Electric field is decreasing as you are moving in the direction of the electric field. Okay, electric potential, actually, even though it is shown positive, actually it is negative. That is the only thing. And this dv by dx denotes that the electric field's direction is in the direction which is decreasing the steepest. Steepest means the straight line direction. That's it. Okay, if you are going in any other direction, the degree of decrease will be less. So only the shortest distance between 2 points is the direction of electric field. That's it. Now derive the expression for capacitance in parallel plate capacitor. Now here we are calculating the the capacitance of a parallel plate capacitor, that is C is equal to A epsilon naught by D. That derivation you have to do. That derivation is super important as well. Here we have a parallel plate capacitor. Suppose this plate is charged to positive, this plate is charged to negative. Okay, the surface charge density for this is plus sigma. Surface charge density for this one is negative sigma. Okay, this is positive, this is negative. Now what? So there will be 3 zones. One zone here, another zone over here, and third zone between the plates. So there are 3 zones. We have to calculate electric field individually for each of the zones. Now, as you know, capacitor plates are basically parallel surfaces. Basically, they are parallel surfaces. One surface like this, another surface like this. They are parallel to each other. This is the distance between them, d. Okay, this is the distance between them. But we cannot draw a 3D diagram always. That's why we are using a 2D diagram. So if you rotate it like this diagram becomes like this. This is a 3D diagram. If you rotate it, this becomes 2D diagram. Now for a single charged plate, for a single charged plate, if the charged plate is very long, the electric field near the charged plate is given by sigma upon 2 epsilon naught. For a very large, infinitely large plate, it is ideal, but for any other charged plate, if the distance is small, this is still true. Okay, so electric field due to a charged plate is given by sigma upon 2 epsilon naught near the plate. So here also the same thing. Now again, as I mentioned, for electric field, the symbol of charge or symbol of charge density is not important. Only thing that is important is the direction. So for a positively charged plate, electric field will be away. Right? For positive charge, electric field will be away. And what is the value of electric field? Electric field for positive should be same as electric field for negative, and that value is sigma upon 2 epsilon naught. The magnitudes are same. Okay, only thing, directions may be same, may not be same. So that's what we have to figure it out. For zone 1, electric field due to positive is away. For electric field due to negative is towards. So same magnitude, opposite direction. So electric field in zone 1 is 0. Okay, same value, opposite direction, electric field is 0. If you go to zone 2, electric field due to positive is again away. This is plus. Electric field due to negative is towards. Again, same value, opposite direction. So electric field in zone 2 is also 0. Now we have to calculate electric field in the zone 3, that is the main zone. But when you are doing it, make sure you show other 2 zones also, and electric field is 0 there. You don't need to write too much, at least diagrammatically, just the way I have shown it here, using the diagram, you can do that in the exam also. Now for inside the plate, this plate is positive, so electric field will be away. This plate is positive, so electric field will be away. This plate is negative, so electric field will be towards. So inside the plate, plus and minus both gets added up. So in the zone 3, the net electric field is basically plus of electric plus E minus. Now what is that value? Sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, that is 2 sigma upon 2 epsilon naught, that is sigma upon epsilon naught. Done. Now what is sigma? Sigma is charge density. So charge density is given by total charge divided by surface area. Total charge divided by surface area. So you can write it here, because for capacitor we use capital Q. So capital Q divided by area. So Q becomes sigma into A. Q becomes sigma into A. Sorry, not Q. The sigma becomes Q upon A. So if you put that over here, you get the electric field in zone 3 becomes Q upon A epsilon naught. Okay, E becomes Q upon A epsilon naught. Now, suppose you have applied a potential difference between the plates as V. The distance between the plates is D. So we know that E, magnitude of electric field, can be written as dV by dx, right? Here in this case, the uh, voltage difference itself is V. So dV itself is V, and the distance between the plate is small d. So and electric field is constant also. So just need to write E is equal to V upon D. So now substitute that in here. So V upon D equals to Q upon A epsilon naught. Okay, or Q equals to A epsilon naught upon D into V. Now, sir, we are trying to find the capacitance. What is this? We have not found the capacitance. Don't worry. For a given capacitor, we know that Q is equal to C into V. So, this is equation 1. This is equation 2. If you compare these two equations, we can say C equals to A epsilon naught upon D. And one very important point, here we have assumed between the plates only air is there. Okay, if there is not air, any other medium, then instead of epsilon naught, it would have been normally epsilon. Okay, and there will be a dielectric constant present. Otherwise, they will not give you a dielectric medium, by the way, only air capacitor will be there. Okay, so this is the derivation, simple, easy derivation. Just follow the step and you will be able to answer this question. Okay, let's move on. Derive the expression for electric potential at a point due to a point charge. One of the most important question from this chapter. If I add a double star, triple star, it is still not enough. Okay, this is the most important superhero question from this chapter. Here you have to have a point charge. You have a point charge Q and you are trying to find the electric field at some point P. Okay, how to do that? First you have to go till infinity and then you have to come back to some point, say A and B. A and B are very close to each other. The distance between them is very small, dx, and the distance of these 2 points from the source charge is x. The distance of the point where we are trying to find the electric potential is r. So this is the diagram and this diagram is compulsory. Now how to solve it? First, obviously, we need to understand that we have to assume the electric field's value, okay, and then we have to start. So if we keep a unit positive charge, okay, what amount of force it will experience, that is given by electric field. So the force acting on a unit positive charge when you keep it at A is given by K Q upon x square, right? This is the distance x. The force acting on a unit positive charge is K Q1 Q2 by r square. Also it is okay. Coulomb's formula if you are using also okay. But one of the charges already 1. So you don't need to worry too much about it. It will be KQ upon x square. Now, now what? Now this is the electric force. So if you want to move this charge from A to B, electric force is acting in this direction. Okay, electric force is acting in this direction. So you have to apply an external force exactly equal to that internal force so that it is moving without any acceleration. So the external force that you need to apply should be equals to minus of Fa, that is minus kq upon x square, minus kq upon x square. Now you have to just construct one integration and solve it. Okay, so this is the external electric field. Now when you move it by a small distance dx, how much work that you are doing? You are doing a work done dw equals to external force into dx. Now why we have to do like this? Because electric field is not constant everywhere. Electric field is changing at each and every point. Okay, so you cannot take a uniform value of the force and every point and do it. Okay, because electric force, whatever electric force is here, that will be different at this point, that will be different at other point. That's why we have to use this method of integration. Okay, so the total work done will be integration of dw, or it will be integration of f external. Now here, because we are calculating the total work done, there will be some limit. The limit is starting from infinity till this point p. So starting point is at infinity, the ending point is at a distance r. So infinity till r f external dx. Now we put the value of f external and integrate it. Okay, so the work done is given by integration infinity till r, and it will be minus kq upon x square into dx. Now minus kq you can take common, integration infinity till r dx upon x square. Okay, now integration, if you are aware of basic integration, you should remember that integration is invert of the differentiation. Okay, so whatever you do in differentiation, integration is exactly opposite. So for example, x to the power n dx, if you differentiate it, it becomes n into x to the power of n minus 1. When you integrate it, it becomes x to the power n plus 1 by n plus 1. Okay, in differentiation the constant directly comes out and the power decreases by 1. In integration, power increases by 1, and the constant that is not coming out as a multiplication, it is coming out as a division, and also that is also increasing by 1. So that is the basic difference between integration and differentiation. Okay, so basically we have to do this integration. So you can write this as minus kq integration infinity till r x to the power of minus 2 dx. So now you see why I have written that integration. Okay, so now just you have to do it. So minus kq equals to minus kq. Okay, integration will be minus x to the power of minus 2. So it will be x to the power of minus 2 plus 1 divided by minus 2 plus 1. And this is a definite integration. There will be a limit infinity till r. This is how we write it. Okay, so minus kq, we get x to the power of minus 1 divided by minus 1 infinity till r. Okay, so it will be, so minus can be taken out and it can be multiplied with this minus. So minus kq, and we have x to the power of minus 1, that is 1 upon x infinity till r. Okay, now what is this meaning of this power? Power is nothing. First we have to put the upper limit minus lower limit. Instead of this variable x, we have to substitute it with this upper limit minus substitute the same with the lower limit. Okay, so minus minus becomes plus. We get kq into upper limit means 1 by r. Instead of x, we put r. Okay, and minus 1 by infinity. Instead of x, we put infinity. Now obviously we know that 1 upon infinity is 0. So 1 upon r will left. So it will be kq upon r. Now this is the work done. This is the work done. Now you have to find the potential. So potential is actually the work done, which can be written as kq upon r, or 1 by 4 pi epsilon naught q upon r. Do not leave your answer over here, because this is the work done. Now, by definition, work done to bring a unit positive test charge from infinity to a point is the potential of that point. So, by definition, you have to write this. This is your complete derivation. This is your complete derivation. Okay, remember this. So, this step has to be shown. Now, few numerical questions. Calculate the potential at point P due to a charge of 400 nanocoulomb located 9 centimeter away. Obtain the work done in moving a charge of 2 nanocoulomb from infinity to the point P. Does the answer depend on the path along which the charge is moved? Very simple, easy question. Don't think it is a difficult question. Calculate the potential at a point P due to a charge 400 nanocoulomb located 9 centimeter away. So, the distance here is 9 centimeter, that is 9 into 10 to the power of minus 2 meter. Okay, and they are asking you potential. Formula for potential is K Q upon R, that is 9 into 10 to the power of 9. Charge is 400 nanocoulomb. Nanocoulomb means 10 to the power of minus 9 divided by the distance. Distance is 9 into 10 to the power of minus 2. 9 cancel. 10 to the power of 9, 10 to the power of minus 9 cancels. So, you get here 400 into 10 to the power of plus 2. This minus 2 goes up, becomes plus, or you write it 4 into 10 to the power of 4 volts. 4 into 10 to the power of 4 volt. This is the potential. Next is calculate the work done to bring a unit positive charge. Calculate the work done to bring a 2 Newton nanocoulomb charge from infinity to that point. This is part A. So, work done to bring a charge at a point in electric field is given by the value of the charge into the electric potential at that point. So, basically, very simply, you just need to multiply 2 nanocoulomb into this potential, and that's it. Nothing else. It will be 8 into 10 to the power of minus 5 joules. Only thing that you have to write is proper units. For potential, it is volts. For work done, it is joules. So, don't make a mistake. Okay, you have to write the proper units whenever you are solving a numerical question. 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination. Find the potential difference across 6 microfarad capacitor if their combination is connected to a 60 volt supply. So, 3 capacitors connected in series. So, in series combination, we know that 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3. Here 3 capacitors, so we are writing this. So, that means it will be 1 by 2 microfarad plus 1 by 3 microfarad plus 1 by 6 microfarad. Now, so far we are not using the microfarad value because equivalent will also come in microfarad. So, all of them are microfarad, right? So, you don't need to worry too much about it. 6, 3 2s are 6, 2 3s are 6, 6 1s are 6. So, 6 by 6, so it will be 1. So, equivalent capacitance will be in reciprocal of that, so it will be 1 microfarad. So, the equivalent capacitance of the combination is calculated. This is part A. Part B, find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. For this part, I might require a diagram. So, here we have the combination of 3 capacitors and they are connected across a battery. So, this one has a say voltage V1, this one has a voltage V2, this one has a voltage V3. Okay. So, you have to find the potential across V3. This is 2, 3, 6. Now, suppose the charge flowing in the circuit is Q. Now, you know that if you draw the equivalent circuit will also have the same charge. Equivalent circuit will also have the same charge, but in this case we know the capacitance. Okay, this is 1 microfarad. So the voltage should be same, that is 60 volt. If you apply the same voltage for a equivalent circuit, the charge should be same. So first we will use this method to find the charge. How much charge is flowing? Q is equal to C into V. C equivalent is 1 microfarad and that is voltage is 60 volt. So that is 60 into 10 to the power of minus 6. In fact, that is also cancelled, but for mathematics you have to show it. This is the charge. The same charge will pass through this capacitor as well. So now, but for this capacitor, the voltage is different. Capacitance value is different. Okay, so same charge will pass through the 6 microfarad capacitor as well. Okay, voltage is given by voltage we are trying to find, and this should be same. Both of these should be same. So it will be 60 into 10 to the power of minus 6, minus 6, minus 6 cancels. So V3 equals to 60 upon 6, that is 10 volt. Okay, in series combination, the charge remains constant. That concept we have applied here. Okay, so 10 volt, that is option. This is for answer B. This is answer B. Now let's move on. In a parallel plate capacitor with air between the plates, each plate has area of 4 centimeter square and the distance between the plate is 2 millimeter. Calculate the capacitance of the capacitor. Take epsilon naught's value is given. If this capacitor is connected to a 100 volt supply, what is the charge on the each plate of the capacitor? So first of all, what is the value of expression for capacitance? It is an air capacitor. So capacitance is given by A epsilon naught upon D. Okay. So area A is given here as 4 centimeter square. Centimeter square means 10 to the power of minus 4 meter square. Remember, 1 centimeter square equals to 1 semi into 1 centimeter. That is 10 to the power of minus 2 into 10 to the power of minus 2 meter square. That is 10 to the power of minus 4 meter square. Okay, remember this. This is a handy conversion. If you can do it, it will save some time. Now, let's put the value of epsilon naught. Epsilon naught is already given 8.854. Now, in some cases, remember, you may need to use a calculator, obviously, because in board papers, they prefer that you finally answer, you calculate using some sort of calculators. Okay, because they are giving you calculators. Simple calculators are allowed. That's why they give you some values which can be used to solve. Next is distance between the plates is 2 millimeter. So distance between the plate is 2 millimeter means 10 to the power of minus 3. That's it. Problem solved. So 2 into 2, 2. Now 2 into 8.854 is very close to 17. It is very close to 17. You can calculate the exact value. I am not doing it. 17 into remember 16, 17, 17.8, I guess. 17.8. It will be very close to 17.8 into 10 to the power minus 4 minus 12 plus 3. So minus 4 minus 12, it goes up and becomes plus 3. So it will be 17.8 into 10 to the power minus 16 plus 3 minus 13. That is 1.78 into 10 to the power of minus 12 farad or 1.78 picofarad. Okay, so this is the capacitance of the capacitor. Okay, very easy. Just put the formula, get the value. Next part, if this capacitor is connected to a 100 volt supply, now you have taken this capacitor and connected it to a 100 volt supply. Okay, then what is the charge on each plate? Very simple. Charge on each plate is given by Q is equal to C into V. So Q is equal to C is 1.78 into 10 to the power of minus 12 into volt power. The voltage that you have applied is 100. So it will be 1.78 into 10 to the power of minus 10 Coulomb or 0.178 nanocoulomb. Okay, you can leave it this way or you can convert it into nanocoulomb. Both are okay. Okay, does not necessarily that you have to show it in nanocoulomb or you have to show it in picofarad. You can leave your answer in 10 to the power values as well. Both are accepted, right? So this is the last question of the day. So almost 3.5 hours almost completed. So let's see. 3 point charges, 3 nanocoulomb minus 2 nanocoulomb and 4 nanocoulomb are placed at the vertices A, B and C of an equilateral triangle ABC of sides 0.2 meter. Calculate the potential energy of the system. Also calculate the amount of work required to place the same charges at the vertices of an equilateral triangle of 0.1 meter. So basically we have three charges placed at the vertices or vertices means these points are called vertices. Three vertex, so that's why plural of vertex is vertices. Okay, three vertices A, B and C, 3 nanocoulomb. Does not matter which way you are writing, okay, because equilateral triangle, so does not matter. So all the distances are same. Okay, sides are 0.2 meter. Okay, now you are they are saying that so the 3 point charges are kept vertices the equilateral triangle ABC. Calculate the potential energy. How to calculate the potential energy of two charges? If there are two charges, potential energy is Q1 Q2 upon R. Potential energy for two charges is given by potential energy due to two charges is given by K Q1 Q2 upon the distance. Now here we do not have two charges, we have three charges. So first we will calculate the potential energy due to these two, then these two and then these two. So basically three charge system can be broken into three two charge system. Four charges can be broken into four two charge, even five two charge system. Okay, so that's a little complicated. Don't go into that. Three charge system is up to that is in your syllabus. So basically it will be K Q1 Q2 upon R, K Q2 Q3 upon R plus K Q3 Q1 upon R. All the distances are same, so I am writing all of them as R. So this will be K upon R Q1 Q2 plus Q2 Q3 plus Q3 Q1. Okay, now let's put the value. K is 9 into 10 to the power of 9. R is 0.2 meter. And Q1 is 3 nanocoulomb. So 3 into 10 to the power of minus 9. Q2 is minus 2 nanocoulomb. So minus 2 into 10 to the power of minus 9. So if you see that all cases 10 to the power of minus 18 will be common. So this is one very important mistake. Sometimes while doing it in the fast way, you do not have too much time. What you do, you just write 3 into minus 2 plus minus 2 into 4 plus 3 into 4. Okay, everything is done. Either you completely forget there is a 10 to the power of minus 18 factor, or some of you even remember there is a nanocoulomb, so it will be 10 to the power of minus 9. But remember, two charges are multiplying, both of them have nanocoulomb. So 10 to the power of minus 9 into 10 to the power of minus 9, it becomes 10 to the power of minus 18. That is very important point to remember. So these are the mistakes that generally many of you usually make. So 9 by 2 into 10 to the power of 10. I have converted this decimal into point so that I just save some time. Now our job is to just multiply this. So 3 to the 6 minus 6 minus 4 to the 8 minus 8 plus 3 4 the 12 into 10 to the power of minus 18. Okay. So minus 6 plus 8 minus 8 plus 12. So if you see that, it will be minus 14 plus 12, so minus 2. So in fact, I don't need to cancel it. It will cancel anyway. So 9 by 2 into 10 to the power of 10. So 9 by 2 into minus 2 minus 14 plus 12 minus 2 into 10 to the power of minus 8. So if you cancel these, it will become 9 into minus 9 into 10 to the power of minus 8. And because we are calculating the energy, the unit will be in joules. The energy will be in joules. So everything is same. Minus 9 into 10 to the power of minus 8 joules. Now the question, second part of the question is slightly tricky. If you don't know how to do it, you might not be able to solve it. Second part is saying that you are reducing the size of the triangle from 0.2 meter to 0.1 meter. Basically, you are bringing the charges closer. And how much work you need to do? For that, you have to find the final potential energy of this system. So this was initial potential energy, say U1. Now you have to calculate the final potential energy U2. Now if you don't know how to do it in shortcut way, you have to start again with all these equation and simplify it. But we have already done 90% of the work. So only thing that you need to do is just in this equation, you change this value of 0.2 by 0.1. Everything will be same. So if you change everything, this 2 value by 1, then your answer is done. You don't need to do any mathematics. So U2 will be 9 by 1 into 10 to the power of 10, right? So for final initial potential energy of the system was U1, final potential energy is U2. We are using the same formula to calculate, only difference the distance has changed. So only thing that we have to do is changing the distance. So we just need to write from the previous equation, we can write the final potential energy to be 9 by 1 into 10 to the power of 10. Now we also know what is the addition of this value. Addition of this value coming out to be minus 2 into 10 to the power of minus 18. So it will be minus 18 into 10 to the power of minus 8. So how much work you need to do? The work that needs to be done is final potential minus initial potential. That is minus 18 minus 9. Okay, minus minus plus 9 into 10 to the power of 18. Sorry, minus 8. It will be minus 9 into 10 to the power of minus 8 joules work needs to be done. So basically the system is shrinking on its own. So the work done will be negative. Don't worry if the work done is coming negative. It can be negative. If potential energies are negative, work done can also be negative. Okay. So also calculate the amount of work required to place the same charges at the vertices of a side 0.1 meter. This is the work done that you need to do. Okay. This is the end of today's session. The PDFs, everything will be added to our course that is available in our channel, in our page. How to access the page? Just go into the YouTube, go into the description section of this session. Once you click on here, okay, once you click on this, join the free second PUC course. Once you click here, you will be redirected over here. Click on buy now, okay, and then your mobile number will be asked. If you have registered once, you will get the OTP. If you have not registered, the mobile number, and then they will ask you to register using your name and some basic details. Once it is done, you just click on this and everything will be available over here, the physics content. So this will be added at the for now I have asked them to reverse the order, okay, but all the lectures are available. You just scroll it down, all the S lectures, S series lectures, all the one shots, as well as all the FA-1 lectures, everything will be available over here. Okay, so just click over here and you will get the entire content list library available over here, and you don't need to search through the YouTube all the different contents there. You might find some 3 years back content as well. This is all latest content, don't need to worry about it, and the PDFs etc will be added on this page itself. Okay, so I request you, if you have not yet registered, go register yourself immediately so that you don't miss out on the class lecture notes and all the lectures that is happening. You might be losing them in the clutter, but yes, if you join it once, that is done, right? So this is the end of today's session. I will be back on Saturday with electric current and moving charges and magnetism. Till then, bye.